Welcome to this tutorial, Reconfigurable Intelligent Surfaces and Holographic Massive MIMO, with the undertitle Vision, Fundamentals and Key Open Problems. I am Emil Björnsson and I'm going to present this entire 3-hour tutorial, and I'm very delighted that you are here and listening. And I'm a professor at KTH Royal Institute of Technology and also at Linköping University, both of them in Sweden. So the outline of this tutorial will be like this. First, I will spend quite some time to provide an introduction to beamforming and wave propagation in general, and talk about the evolution of multi-antenna technology, which is sort of the basis behind both of these two concepts, reconfigurable intelligent surfaces and holographic MIMO. Then, I will talk about, in particular, the reconfigurable intelligent surfaces, the fundamentals and the vision behind that technology, the system model and optimization. We will go into this in particular detail because I think this is important to understand the underlying theory in order to understand what we actually can do with this technology and how it's implemented. Then we will talk about holographic massive MIMO, which is much more related to conventional MIMO technology, which means that we can reuse a lot of the result, but there's also new phenomena that are appearing in those cases. So I will talk about those properties and benefits. And then I will talk about spatial channel modeling, which becomes very important to consider when we have big surfaces of either of these two kinds. And those channel models are applicable in both cases. Then I will talk about open problems, such as what are suitable use cases for these two different technologies, and how can we do channel estimation. That's also an important open problem. And then we will reach the summary. So let me start now with the introduction and with some of the just basic wave propagation. So electromagnetic waves is what we use in wireless communications. They're traveling at the speed of light. They spread out in all directions. And suppose we have a transmit antenna, which is isotropic, which means that it spreads out the energy in all directions equally much. Then, when we are considering a distance d from the transmitter, the energy will lie on the surface area of a sphere with radius d. And if we have a receive antenna at that distance and it has an area focused towards the surface area of the sphere, which is a, then we can compute the energy that is received, or the received power, which is going to be the size of this receive antenna, the area A, divided with 4 pi d squared, which is a total area of this sphere. And why do I bring up this? Well, we have this classical propagation formula for line of sight communications. Transmit power is equal to this ratio. That gives us the receive power. And if we consider typical numbers here, say that the area is computed as taking the wavelength divided by 4 and square it, so you have a wavelength divided by 4 times wavelength divided by 4 sized metal sheet that is receiving the energy, and that we have a typical 5G frequency of 3 GHz. Then if we put in a distance of d here being equal to 1 meter, we will receive 0.005% of the signal energy. And that is a path loss of minus 43 decibels. And if we increase the distance by a factor 10 to 10 meters, we are losing another 100 times of energy. So 0.00005% of the transmitted energy is received, which is minus 63 decibels. So if we take the transmit power, divide it up into 2 million pieces, we are then only receiving one of them. So there's a lot of losses along the way, and this is typical in wireless communications. The reason that it works anyway is because we are comparing the received signal energy with the noise power. So that is what we're used to, but since it's only a tiny fraction of transmit power that is received, tiny changes in how we are radiating our energy can also lead to large changes. So if we consider a conventional base station antenna from the 3G, 2G, and also to some extent 4G, we are using this kind of sector panels that are radiating energy directive in a particular direction. So instead of spreading it out in all directions, we are deciding on that, well, most of the use are going to be in the center of a sector, down on Earth and not up in the sky. So that's why we can use a so-called 16 dBi gain antenna, which is focusing the signal energy towards the center, and there we have 16 decibels stronger signals than in my previous example, which means 40 times stronger. And if you're a lucky user standing there in the center of the cell area, then you get that 40 times stronger signal, which can make a lot of difference in terms of what data rate we can deliver to the user. The problem is that it's still the same transmit power that is radiated, so it's just that it spreads out unequally in space, and it does it in a predetermined manner. So if you happen to also be in the same cell area, but you're behind this building here, so you will need the signal to bounce off this building to reach you, well then you're an unlucky user, because that propagation path is outside this focused area. So the base station antenna has essentially taken energy from your direction and put it into the center of the cell, because that is where you are expecting the users to be. So the unlucky users are not having a benefit of the focusing, and they might even lose from the focusing because we're taking energy from some directions and put them in other directions. So how can we improve the coverage in a scenario like this? Well, there are basically two things that we can do. The first thing is to control the transmission in a different way. We could make sure that we are not always transmitting in this direction, but sometimes we are transmitting in this direction as well. And that is what we have been doing in recent technologies. In 4G and 5G, we are controlling transmissions, and we will look further onto how we do that. The second option is to control the propagation environment. How can we control it? Well, we can put up some additional equipment here, or we can select what kind of materials that exist, or we can essentially move around our base station and select where to put it so that we are getting good propagation conditions. But the new concept of reconfigurable intelligent surfaces is focusing how to improve the propagation, and we will come back to this in the tutorial. And also when it comes to holographic massive MIMO, this is technology to put at the base stations. But let's start from the fundamentals and talk about how we are forming directive transmissions by constructive interference. Here I have two different antennas, and suppose they are transmitting the same signal at the same time, like this. We see that the wavefronts are spreading out. The green wavefronts here radiate at the same time, the gray at the same time, the orange at the same time, and so on. And if you are standing at a location where these wavefronts are intersecting, this is a location when the signal transmitted from these two different antennas will reinforce each other. You receive them in phase, and therefore you get a stronger signal at those locations. And this is happening here in this direction, and this is what we call constructive interference. You have two signals that are transmitted, they are the same, they are interfering with each other, but not in a bad way, in a positive manner, so that we are getting stronger signals in these directions. But that also means that there are other directions where we have destructive interference, where the two signals are cancelling out each other partially. So what is happening here is that we are generating this kind of constructive interference and focusing in a synthetic manner by taking two antennas. Both of them are radiating the signals uniformly in all directions. But by transmitting the same signal at the same time from these two antennas, we are effectively focusing the signals forward in this case here. And that is what we call beam forming. If you would like the beam to go in another direction, we can do that. This is just how the conventional base station antennas with the fixed directivities has been operating, by having multiple small antenna elements within the box and feeding them with the same signal. But suppose we let the right antenna here transmit a little bit later than the first antenna, the left one. Then we see that there are other locations where the wavefronts are representing the same signal are intersecting. So the green signal here have traveled further towards the right compared to the signal here. So we see that there are these locations here where we now see constructive interference, and we are essentially focusing the signal partially towards the right here. So what we are doing now is that we have two antennas. They send the same signal but with different delays, and that is enabling us to achieve constructive interference in a direction of choice. So this is how beamforming is done. So if you would like to from a base station direct signals in a particular direction, you have a multitude of antenna elements that radiate the same signal but with different delays. And by having this kind of directive transmissions, we are getting what is called an array gain. So if you have two antennas that are radiating the same signal but with different delays, in the direction where the delays are adding up constructively, we get twice the amount of signal there, even if the total energy of the two antennas here is the same. So we take the power, we divide it equally between the two antennas, we're transmitting it in such a way that we get the focused beam in one direction, and there we get twice of the energy. And of course we have less energy in certain other directions, like in this direction. If we have 4 antennas, we are transmitting from all of them. We are taking our total power, divide it equally between the 4 antennas, and then we select our delays so that we form a beam in a particular direction. Well, now I've drawn a larger beam because now we have more focusing in that direction. We have 4 times the signal power in the main beam direction here. If you have multiple antennas, what you also can do is to transmit multiple signals at the same time. So in addition to take the blue signal here, I can also say that I would like to transmit to another direction, create a red beam like this. That is created by sending the same signal, but a different one from the blue one, but the same signal from all the antennas, but with a different set of delays, so that we get constructive interference in this direction. And that will then enable us to transmit multiple signals by taking how we would compute the blue one, how we would compute the red one, add them up on every antenna, so we get a different weighted summation of the two signals, also with different delays. And of course we are then dividing the power between these two beams. So if we have 4 antennas in this case here, you can see that we get essentially the same beamforming gain as with 2 antennas, because we are getting 4 times the beamforming gain, but we are only having half of the power for each of the 2 beams. And you can do this also with 2 antennas. You can send multiple signals, like 4 signals in this case as well. There are many ways of doing it, but the important thing is that this is how we are generating directive transmissions and also enabling us to transmit multiple signals at the same time. And similar type of things are happening when we're considering how waves are behaving when they're hitting different surfaces, when they're interacting with objects. So suppose we have a flat surface here, like a mirror. It's a large mirror. We can even say it's infinitely large. And we have a signal that comes in here. It's a plane wave moving from the right. And it goes like this. 2 parallel rays are shown here. And since the plane wave here is hitting the surface at different times here, because it is further to this location and to this location, something happens. The signals get reflected down like this. And we might be familiar with how this should happen according to Snell's law, that if a signal comes in with a certain angle, it should leave with the same angle but on the other side of the normal, which is what is shown over here. And one way of viewing what is actually happening here is something called the Fresnel principle. Namely that you take your surface here, you chop it up into small pieces. Every piece, you view it as an antenna. So the signal is reaching this point here, and then immediately it gets re-radiated in all directions. So it's like an antenna spreading out this energy. And the same thing happens here for the red signal. You have one point here where the signal energy gets captured, and then immediately it's re-radiated due to reflection. And then when you are doing this kind of trick with every element here, you take your big surface and chop it up into small pieces. Then you have many different small antenna-like objects here that are radiating signals, and those objects will create constructive interference in a particular direction, namely downwards here. Because if you're measuring the length of the blue path and of the red path here, they're equally long. And that is why we get constructive interference in this particular direction. And when you have infinitely large surfaces, then if you have a plane wave that comes in, you have a plane wave that goes down like this. But if you have a finite sized surface, then what is going to happen is that you get a signal that comes in. Ideally, it's a plane wave with just one wavefront moving like this, and it hits the surface, and then it gets not a plane wave that is reflected, but a beam in this direction, because we have a limited number of different small points on the surface here. And whenever you have beams, what I talked about earlier was that the more antennas you're having, the more the signal gets focused, and one can say that the beam width is inversely proportional to the surface width. So when the surface gets infinitely large, the beam becomes infinitely small and narrow, and that is when a plane wave that comes in will also create a plane wave that goes out. But in general, when objects are reflecting signals, it's not in the form of a plane wave, but in form of a beam in a particular direction. So this is how reflection is happening, and it is sort of like having an antenna array here that's re-radiating the signals. And the direction of the beam is determined by the geometry here. And we should remember this, because this is what we will utilize later on by adapting the surfaces in order to control how this beam is behaving. We will now talk about the evolution of multi-antenna technology, focusing on how we are using multiple antennas in the systems of today and how we have been reaching to that point. So the idea of transmitting from multiple antennas with different delays in order to create directed transmissions is nothing new. It has more than 100 years of history. So you can, for example, find this patent from 1920 by Ernst Alexandersson, who is a Swedish researcher who was working in the US at General Electric at the time. And he was creating the first technology for doing this. It was utilized during the First World War to communicate over the Atlantic. And you can still find in Sweden the Grimton radio station, which is a UNESCO World Heritage Site containing multiple antennas here that were utilized in order to communicate with the US over the Atlantic. And the idea of using multiple antennas not only to focus energy, but also to serve multiple users at the same time. This is something that was appearing in the late 80s and early 90s, and it was then called Space Division Multiple Access. Nowadays it's often called multi-user MIMO, where MIMO stands for multiple input, multiple output. And the patents for these type of ideas was submitted in the early 90s, and it was particularly about having base stations serving different cars here, because at that time mobile phones were actually car phones. And you can see this was a cellular network where you had base stations at different locations serving different users. And at the time when this concept were created, then we didn't have an information theory behind how we would build it. So it was more of an engineering effort than something that was built on some rigorous mathematical theory. The motivation is really that the data rate that you can deliver over a certain frequency band increases with the number of antennas at the base station and with the number of users that you can serve at the same time. So here's an example where I'm changing the number of users from 1 up to 20, and I'm showing the sum spectral efficiency in bits per second per hertz per cell. And we're considering some simple models here. We have ID Rayleigh fading, we have 0 dB SNR for every user, and we have a signal to interference ratio of 10 decibels. So it's a fairly low signal to noise ratio, but you can see that I have different curves representing different cases. In all cases, when I add users to my system, I'm also adding antennas to the system in order to direct the signals better and better towards them, and to be able to, at least you need to have as many users as antennas, or antennas as users, so that you can form different beams that are non-overlapping towards users. This is how the sum spectral efficiency is increasing essentially linearly with the number of users when you have the same number of antennas as users. So that is enough in order to deliver what we call the multiplexing gain. However, in practice, it's also important to make sure that you are able to cancel interference between users. And that is enabled by having multiple antennas. In particular, when you have more antennas than users. So if you increase the number of antennas by factor 2, so you have twice the number of antennas as users, you get this curve. 4 times or 8 times. And you see it's increasing like this, and up to a certain point where the benefits are not that large any longer. But the main thing is that we would like to serve multiple users from the same location, and we can do that by adding antennas so that we can separate them spatially with different beams. Later, there was also the idea of serving one user with multiple layers of data. This was called layered space-time architecture. Nowadays it's called single-user MIMO. And it's a concept and patents from the late 90s. So it was 5 to 10 years later. And information theory for this type of method was showing up around the same time. And here you can see an illustration from an early paper where there were multiple antennas at the radio port, multiple antennas at the remote unit, and the idea was then that there are multiple propagation paths. So one direct path, one that is reflected on different objects, and one reflected on this mountain here. And one way of viewing it is that you send different beams along different paths, but you can also send them in such a way that you are maximizing the capacity at this receiving location. At the time when we were developing this kind of concepts, the goal was typically not to increase the data rates, but to try to multiplex as many phone calls as possible. So that's why the idea of serving many users appeared before the idea of pushing up the data rates. But it's the same benefits. You get the multiplexing gain. You can send multiple signals at the same time with different data. And I would say that this kind of ideas have gone from being a bit science fiction-like to mainstream over the last decades. So in the 1990s, there were early deployments of MIMO technology in Japan and Korea, for example. Here is one example where there is a circular array, and you can see that you have antennas, you have antenna cables, you have amplifiers and radio units underneath. And it turned out that this type of technologies were only deployed in a few countries because it was easier to deploy more base stations than deploy fewer base stations with more advanced hardware. And at the time, it was typically too small to see the benefits. You had approximately the same number of antennas as users because that seemed the reasonable thing to do. Why have too many antennas if the multiplexing gain that you can achieve is proportional to the number of users and not the number of antennas? And there were no information theory behind it, and at the time, as I said, voice call was the main application rather than data packets. So as long as you can deliver a minimum SNR so that you could hear what the other person is saying, then you didn't benefit from having higher data rates. So based on that experience, there were a lot of skeptical voices when we were talking about pushing MIMO technologies as a 5G technology. People were saying it will be too large, need too many antennas, too expensive, too much equipment they need to put on site, too high computational complexity, the practical gains are very small, and so on. But now we can see that MIMO technology is sort of one of the key things in 5G. And among all the things that people have been saying that 5G will contain, so far, what it does contain is massive MIMO in the 3 GHz band. Barely no millimeter wave or other kind of new use cases, but it's spatial multiplexing with MIMO. That is the main thing so far. And one can see that there are plenty of different massive MIMO products available on the market for different frequency band, for different sizes, transmit powers, and so on. So going from 16 antennas, 32, 64 antennas, and some certain products that are integrating multiple bands in the same device, and so on. So what has really happened in the base station development in 5G is that we have gone from having the main type of base stations, one high gain antenna that maybe have 16 dBi antenna gain, 40 times stronger signal in the center of the cell, and it's a passive antenna with constant directivity, to having this kind of 64 low gain antennas in one panel like this. So two-dimensional surface with multiple antennas. You see this 8 times 4, and then there is a cross here which is saying that this is a dual polarized antenna. So two antennas at the same location but with different polarization of the waves that they're radiating. And the main thing here is that these are so-called antenna integrated radios. So within the array here, there is both the passive antenna units and there is the radio units that is creating the signal that should be radiated. That is where we can create the delays of different signals, and that enables us to send different beams to different use at the same time. You can have many more antennas here, 64, so you can get narrower beams, and you can adapt the directivity and separate uses and space and so on. And this is what is nowadays called massive MIMO. And the definition of massive MIMO is a bit hard to specify because it means different things for different people. So in the industry, I think nowadays everything that have more than 16 or more antennas is considered massive MIMO. While when Thomas Marcetta was inventing this type of idea and presenting it in a 2010 paper called Non-Cooperative Cellular Wireless with Unlimited Number of Base Station Antennas, he was rather talking about an unlimited number of antennas. But in my book, Massive MIMO Networks, the way that we like to define it is to say that we have a cellular network like this, with many antennas. There are M antennas per base station, where M should be at least 64. I think that product with 16 or 32 isn't really massive MIMO in the way that we have been thinking about it. And the technology should be capable of spatially multiplexing at least 8 users. And the important thing is then this antenna to user ratio, which is greater than 1. Here it's 64 divided by 8, then you have a ratio of 8. And of course, when you have deployed a certain number of antennas, the number of users that you actually have in your system will vary depending on the hour of the day, and maybe you have 0 users at night and you might have 8 or more users in the peak hours. So massive MIMO is a reality. There is 1 million massive MIMO base stations deployed. How massive is it? Well, I think the word massive might not be a good one because it sort of gives you the feeling that there's a big piece that is heavy. But here is the latest massive MIMO product from Ericsson that was described in March 1, 2021. They call it the Air 6419, contains 64 antennas, 64 radios, connected to 192 antenna elements. This means that every antenna is actually connected to 3 radiating elements, which is creating some kind of fixed directivity within that type of small subarray. Anyway, the whole thing is weighing 20 kilo, and it can transmit 320 watts over 200 megahertz of bandwidth, which is an impressive thing. It's for the 3 gigahertz band, and it has integrated circuitry that is doing all the computations. So essentially, this is what people who have been working with massive MIMO in theory have been imagining for a long time, and now it's actually a reality. So does this massive MIMO product now that exists perform as expected? Well, to have a closer look at that, let's look at some simulations based on real like ray tracing models. This is for a city. It's inspired by New York City. We put up base station at several locations, and we put out users in different buildings, and we are computing the actual channels that we're getting. And what's important here is that we need to consider something called spatial correlation, namely that the array geometry is determining how the channels to different users will look like, and also angles and shapes of different objects in the propagation environment is important. And this was something that Thomas Marcetta was not caring about in his first paper. He considered the simplest model where all of the different channel components are independent and Gaussian distributed, known as the independent Rayleigh fading model. And here we were actually computing by ray tracing the models. We had 16 cells. We dropped 9 users per cell area. It's a 3.5 gigahertz band, so a real 5G band, 20 megahertz of bandwidth, 43 dBm per base station that we're transmitting with, and then we have state-of-the-art processing from my book, Massive MIMO Networks. Regularized zero forcing, and we allocated in power in the downlink based on maximizing the product of the user's signal to interference and noise ratios. And what I'm showing here is what downlink throughput that the users are getting as they are moving around or placed at random locations. So there is a large variations created by this randomness of where the users are and where the co-users are, which is also sort of creating interference in the system. And there are 3 different curves representing 3 different ways of generating the channels and selecting the panels. The one thing is Marchetta's baseline with this independent and identically distributed or IID Rayleigh fading. Then we have 2 deployments, one with the plane array, looking a bit like the array that Ericsson was actually building. Here we have 24 times 8, so it's 1 meter times 0.34 meters. And you see there's a 192 element here, just as in the Ericsson product. Even if they only had 64 antennas, here we have 192 antennas. So we also have one benchmark with a long linear array horizontally. It's 8 meters long and very thin because we have all of the elements with half a wavelength spacing horizontally. And what we can see in these curves here is that in the upper part here, where users get high data rates, they are all around the same locations. So lucky users will have a small difference between the 2 practical way of building antennas and using the practical ray tracing models and Marchetta's baseline model. So there, the practical massive MIMO is working as it's meant to be. But if we go down here, we can see that there is this large difference. So unlucky users can lose a lot. So the black curve here providing the largest performance prediction is Marchetta's baseline, while the long uniform linear array is providing something that is not that far off, while our planar array is far off. And this is actually what is being built in the networks of today. So what this means is that we need very large horizontal arrays, physically large arrays, in order to be able to separate the users. Why? Well, because even if you put out the users in a city with some variability, this is like New York City with tall skyscrapers, most users are not separable by having different directions in the elevation domain, but actually being located in different directions horizontally. So typically a base station is covering something like 120 degrees. And even if users can be moving up and down, there is much less variability there. So we need large horizontal arrays to actually get performance everywhere in your area that is resembling what we have been calling massive MIMO in the past. So I would say we are far from truly massive MIMO systems. So what I'm showing here is the spectral efficiency in bits per second hertz per user that you can get depending on how many number of horizontal antennas we have in our network. And the dashed line here is representing what Marchetta was predicting in his papers. And in his paper 2010, he was seeing that as you add more and more antennas into the system, what is happening is that eventually you converge to a maximum spectral efficiency that was determined by something called pilot contamination that is limiting the performance. Namely, different users transmit the same pilots at different places in your network, and then you have not enough ability to separate them, so you will interfere between those users. Even if you add more antennas in the system to get narrower beams, you always leak to those ones that have channels that are estimated using the same pilot sequence. But what we were showing in a paper called Massive MIMO has Unlimited Capacity is that the spectral efficiency is actually going up. When? Well, when we are using that true channels are not IID Rayleigh fading, they are correlated in terms of the fading. And when you have a system with uncorrelated fading, as Marchetta was considering, then what is known as maximum ratio processing, where you are only focusing the beams directly towards the users, that turns out to be a good option to utilize. There is not much need for trying to cancel out interference because you're still limited by the pilot contamination effect. But when you have correlated fading and you are using methods that are cancelling out interference, you can get much better performance. And the difference might not be so small down here where we are today with 5G base stations, where you have like 8 or 16 antennas per row. But when you are moving up in number of antennas horizontally, if we can build large arrays, then we can see a big difference in terms of being able to separate users in an entirely new way, provide many users good performance, and utilizing the spatial properties of the channels. And if we would like to build large arrays, there's really two different ways of doing that. One is to build active arrays. Big active arrays similar to a massive MIMO base station from today, but much larger. And even if massive MIMO was from the beginning considered to be a setup where we have many antennas, the antennas went to infinity in Marcetta's first paper. Since we now have products for massive MIMO where we have 64 antennas or so, when we are nowadays considering much larger arrays, we have decided to use new names for that technology. There is the name Holographic Massive MIMO that I'm utilizing in this tutorial. People have also talked about large intelligent surfaces. And there is also something known as Reconfigurable reflect arrays, where you have antennas that are sending the signal towards a neighboring surface, and then that surface is beamforming the signal in different directions. But the main thing here is that you have an array, you have radio units, they are at the same location, and you utilize them in an active manner, so you're transmitting the signals and form the beams at the same location. Another option is something called semi-passive arrays, and this is what Reconfigurable intelligent surfaces is about, where you have a signal transmitted from one location, you have an array located at a different location, and this array can reconfigure its properties to reflect signals as a beam towards a desired location, like the user here. And intelligent reflecting surfaces is another name, software controlled meta surfaces is yet another name. There are many different names for this type of technologies. But the important thing here is that we have a physically larger arrays than in current technology, and we can utilize it in new ways. And this is what this tutorial is going to be about. Both the active arrays called Holographic Massive MIMO and the reconfigurable intelligent surfaces that are passive. And we will have a lot of focus on this passive case because they are much more different than the active arrays compared to existing technology. So we will now talk about the fundamentals and vision of reconfigurable intelligent surfaces, and in many cases I will abbreviate this as RIS, R-I-S. So consider once again a case where you have a base station transmitting a signal, we have a user somewhere, and the direct path is blocked somehow. Blocked doesn't mean that there is no signal coming there, it's just that we have a poor signal. So if you remember the first example I was having when I was computing path losses in line of sight scenarios, then here you might have a line of sight plus a loss due to the wall penetration of 20 decibels or more. So the signal that goes directly here will be weak. However, we have a window here where the signal could potentially move through the window without any large losses. The problem is that the signals will then reach the wall here, and when it reaches the wall, there are the behaviors of reflection and scattering. Reflection is approximating that the signal is just changing the directions, and scattering is when you have a surface that is rough, and therefore different pieces of the surface here will reflect the signal in different directions, and therefore they are creating some kind of scattering behavior. So the problem here would then be that even if this is a smooth surface, what will happen is that the signal will probably be reflected towards the right part of the room. And if it's a scattering, it will spread out over the entire room, but the part of it that will reach me as a user will not be very large. So maybe the direct path through the wall will still be stronger. A reconfigurable intelligent surface is something that we can deploy on the wall here, with the idea of taking the energy that is reaching that point, and instead of just randomly send out the signals either to the right here or spread it out of the room, we can control how the signal gets re-radiated, in this case as a beam towards me as a user. And the word here, reconfigurable, means that the properties of the surface can be changed over time. Intelligent means that it's real-time programmable, so we can design algorithms that are determining how we are reconfiguring things. And surface is indicating that this is a two-dimensional array of small scattering elements. So it's always a two-dimensional thing. And here's an example of how a reconfigurable intelligent surface could work. We have a transmitter sending out the signal. It reaches the surface here, and the surface is configuring itself in such a way that it creates extra delays to the incoming signals to form a reflected beam towards one user 1 here. And then we have a controller that can then change the beam direction towards user 2, which is me. And then I get a strong signal, and then we can jump back and forth like this. And it's this programmable controller that is doing all of this magic. So the surface is containing many small passive patches, like an antenna. But we don't have a radio connected to it. Instead, we terminate it, and we have a switch that can change properties of it based on this controller here. What kind of properties? Well, the impedance of the element. The impedance is determining something called the reflection coefficient, which says that when an incoming signal comes and before it gets re-radiated, it will be delayed and will have a change in amplitude that is determined by the impedance of the element. And by creating an impedance pattern like this, illustrated by different colors, we can change the incoming wave's properties. Some elements here are delaying the signal more than the other ones, and that is then creating other types of constructive interference than the surface would do if all of the elements had the same impedance. And that is sort of how we are once again creating directive beams in certain directions. Remember, when you have a flat surface, metal surface, signal comes in from one angle, and Snell's law is telling us that the signal goes out in the same angle but on the other side of normal. And now we can change that by creating additional delays in our surface by having different impedance in different parts here. And the idea is that this surface should approximate having a different shape than it actually has. And each element here have a sub-wavelength size. So why is that? Well, ideally we would like the impedance to change continuously like this over the surface. But that is hard to build. So instead we can take the surface and we can discretize it into small elements. And the idea would then be that every element have one color here representing one impedance value. And how large should elements be? Well, suppose the signal comes in from minus 30 degrees. Then Snell's law tells us that it should go out in plus 30 degrees. And that is what is going to happen. But it's only when the surface is infinitely large that we get something that is sharply comes in from one angle and leaves in the same angle. So suppose that we have half a wavelength times half a wavelength as the size of our element. In that case, we get a red curve here showing that how much energy that is re-radiated in different directions. And we have normalized the gain here to 1 on the average. And we can see that at plus 30, where we are expecting most of the energy to go, most of the energy is actually there. But it's still a variation here. So we are sending a beamed signal in the main direction, 30 degrees. When we reduce the size to a quarter wavelength times a quarter wavelength, we get the blue curve here. And we still have some directivity towards 30 degrees, but the variations are much smaller in the gain of the signal, different angles. And if we go down to the wavelength divided by 8 times the wavelength divided by 8, we get the black curve here, which is almost flat. So we want each element to scatter signals almost isotropically so that we can control the direction of the radiated signal, not because the element have a preferred direction, but because we can change the impedance pattern so that the different signals, all of them get re-radiated in all directions, but we get constructive interference in a direction that we can choose. If the main idea with a RIS is to take a signal that comes from one location and re-radiate it or reflect it towards another location, then you might be familiar with that there are other technologies doing the same type of thing. A traditional thing is a passive repeater. So that's something that we can utilize, for example, at the countryside. We have a base station at one location, elevated, but not elevated enough so it reaches down in every valley. So we have a shadowed direct path here. And then one can put up a big billboard, passive metal surface called a passive repeater, that is located at a selected location to have line of sight to the base station, and then you direct it so that the signal will get reflected down in the valley where the users are. And the good thing with the passive repeater is that it's fully passive, no power consumption, anything. It's just is a metal sheet that is located so it reflects the signals. The problem is that it will have a fixed beam pattern. It will always radiate the signal down into this location here, and that creates a trade-off between, if you make it too large, then we will of course gather more energy, but it will be focused much more down into just a single direction here. The beam will be narrower, so we need to sort of select where we would like to use it to be, and if they're somewhere else nearby, then we might not get the same kind of beamforming gain. So a reconfigurable intelligent surface is something we could deploy at the same location, but now we could instead change its properties over time. We can have a stronger beam, which is more narrow, but we can change it depending on if we are serving this user or this user. So stronger beams are possible, but we must control the signals. And at least when we are reconfiguring the surface, we require some power consumption. And the whole idea of having additional pieces of equipment that are improving the propagation conditions, transmitting from a source to destination, have some kind of entity that is controlled in the radio environment. This is something that has for a long time been known as cooperative communications. And one can create a taxonomy of different cooperative communication methods. One can talk about regenerative and transparent. Regenerative are methods where we are taking signals and we are taking them from the analog domain to the baseband, and then we are creating new signals and retransmit them. And transparent, which are signals, cases when we are just processing the signal in the analog domain, we are not doing anything particular with them, and then the receiver doesn't need to know about the existence of the signal or about this piece of equipment. It's just changing how the signal is propagating over there. One can also talk about half duplex equipment, which are transmitting and receiving at different times, and full duplex equipment that are transmitting and receiving at the same time. And some options is what is known as relays. There is amplify and forward relays, which are typically half duplex transparent relays. So they are receiving an analog signal and then they are amplifying it and re-radiate it. There's also decode and forward relays, which are receiving signals, decoding them, and then re-encodes them and retransmits them as if they were the transmitter from the beginning. Then there are full duplex equipments that are both amplifying and forwarding the signals at the same time, or decoding and forwarding the signal at the same time. They can transmit and receive at the same time, but typically it still takes the signal, processes it, and then retransmits it. And then we have the category of full duplex transparent relays, which are containing the classical passive repeaters, but also the new technology of reconfigurable intelligent surfaces. And it's not about that one is better than the other here. They are made for different use cases. So we need to figure out what this new idea of reconfigurable intelligent surfaces is inherently good at compared to the existing toolbox of cooperative communication methods. And the vision is really to create a controllable propagation environment. And remember, I was showing you this location or setup before, where we have a base station transmitting, we had a user behind the wall, and we had two locations where we can improve things. And we can put up base stations, like massive MIMO base stations, to direct signals towards one location. Then we can put up reconfigurable intelligent surface to reflect the signal as a beam towards me as a user, and they will then cooperate in order to give me a stronger signal. And the idea with the reconfigurable intelligent surface here is that it as a whole can control the directivity of the scattered signal. It can also control signal absorption and change polarization of waves. There are other things that can also be done using this kind of surfaces, which are typically made of things like metamaterials that are hardware implementations where we can change impedances and other properties. We can use it for improved indoor coverage. So here is the library at Linköping University. Suppose we put a base station at the top here, radiating downwards, well then the signal will not reach into different floors here. So we can put up these surfaces to receive signal from above and then reflect it into different parts of the different floors. And outdoor, there are definitely some base stations in the city here, and suppose that I am standing here in my hotel room and cannot see any of the base station. There is no line of sight path. but I can see some locations that the base station can also see. So we can put up surfaces there, configure them to reflect the signal from a base station into my hotel room. So the vision of reconfigurable intelligent surfaces is really to create a controllable propagation environment. And we will look deeper into the performance benefits that we can obtain from that, but first we need to develop a system model for what we call RS-aided communications. And we start from basic signal system theory, where signals are represented in the passband as a signal I call x of t. And if we are sending a passband signal through a system, then we get the received signal y of t. PB is standing for passband here still. And what typically happens when the signal is sent through a system is that it becomes filtered. So if we have a passband signal focused around the carrier frequency Fc, and we have a bandwidth B, well then the signal first have one frequency spectrum, and the blue signal gets a change of the frequency spectrum. The blue one here, it's still in the same band because systems are linear, but it will have a different shape. So that is sort of what the communication channel, for example, is doing. And if we have a linear time invariant system, we can characterize the system by an impulse response called h of t, and then the received signal is the convolution between the transmitted signal and this impulse response, which is computed using an integral expression like this. And communication channels are systems or filters. So for example, you have an antenna here transmitting, you have a receiver here receiving signals. There are three paths: a direct path, and that path means that we have a certain delay, tau 1 of the signal. We have a certain amplitude loss, rho 1, and we have a square root here as well. And then we have a signal that goes through the building here. It gets reflected. We have a longer path there, so we probably have a longer delay. And we have another amplitude loss here. And we have one signal that is bouncing off its building. It has one delay and has one amplitude loss. So we get 3 copies of the transmitted signal, and they have different amplitudes, different delays. And if the transmitted signal is a impulse, namely a Dirac delta function, then if you replace x here by Dirac delta functions, what we will then get is a impulse response, which is the amplitude multiplied with the delta of t minus tau 1, plus the corresponding amplitude loss, another delay, and one loss here and one delay. This is essentially how we are characterizing the signals that are coming from a transmitter receiver as a summation over different signals, paths that have different amplitudes, different delays. And when we are analyzing communication systems, we are typically not doing it for one particular carrier frequency, but we are moving signals from the real passband, where the signal is being transmitted, to a complex baseband where we can have an equivalent representation of the system that is the same irrespective of where we are putting our signals. So we can use the same communication theory for any frequency band. And the way of doing that is to downshift signals to the origin. So we move the signal all the way down, so it's centered around 0. And now, if we had a real valued signal before, that was symmetric, not symmetric around Fc, but it was located here in B. Now, we have a signal that is centered around 0 and is not symmetric. The frequency response is not symmetric, and the frequency content of the signals are not symmetric. So that means that we are getting a complex valued signal, but it also have half of the bandwidth because we're only counting from 0 in the middle here up to the largest positive frequency. So that is what happens when we're moving things from the real passband to the complex baseband. We get half of the bandwidth, but we get something that is complex. So it's the number of symbols per second that is representing the signal is still the same. And the connection between the passband signals with PB as subscript and the complex baseband signal without PB can be written like this. You take x of f you are moving it up to plus carrier frequency, and we have a negative part as well. We add them up and we get the passband signal. And we can do the same thing for the received signal. They're connected like this. This is standard signals and systems theory. And while our communication channel is appearing in the real passband, we typically are modeling them in the complex baseband as well. So we want to have a corresponding input-output relation like this. We are transmitting a signal in the complex baseband, we get the signal in the complex baseband that is received, and we would like to have the received signal as a convolution between the transmitted signal in the baseband and some kind of impulse response. And the impulse response that we get will be the same as before, one we had in passband, but just downshifted to the baseband. So we multiply with e to the power minus j 2 pi fct, because that is what happens when we are moving something back and forth in the carrier frequency. And we should remember that when we are now analyzing reconfigurable intelligent surfaces using this theory. So we have a transmitter sending a signal to a surface with n elements, and that surface is re-radiating the signals, but it's incurring some kind of changes to it. They are filtering them, and then we get a received signal. And the end-to-end system can be modeled just as before. We have a passband signal that is transmitted, we have a received signal that is received, and then we have a big box that is describing what is going on the way there. But if we look into the box, what we can see is that there are n plus 1 different paths showing up. We have one direct path, or at least something that doesn't go to the RS. It could be a line-of-sight path, but it can also contain a lot of other scattering of the signals, that ways of making it to the receiver without involving the RS. And that's something called direct channel here. We can also call it the uncontrollable channel. So it's just described by one impulse response like this, HD of passband of T. And then for the transmitter to element 1 in the RS, we have one channel to element 1. It has an impulse response. We write like this, A1 passband of T. Within the surface, there is something happening. Namely, there is some processing of the signal. The impedance of the element is processing the signal. We can represent this as an impulse response like this as well. And then the signal gets re-radiated, moves over there to the receiver, and there is one impulse response describing that. I call it B1 passband of T here. And then the same thing happens for all of the elements. We assume that they are not coupled in any way. The signal are just going over one channel, get filtered by one element and re-radiated again, and then it continues like that. And there is then n re-radiated signals. There's one direct signal, and they are added up over there, and we get the received signal. So the end-to-end impulse response is a summation over the impulse responses of these different paths. We have the impulse response of the direct path, and then for each of these paths here, we have a summation over them, and we are having one filter here, and a filter is creating an impulse response, and that takes the transmitter signal and convolve it with this impulse response. If we take its transmitter signal and multiply it or take it into the next box, we will get another convolution and then another convolution. So the effective impulse response of these three different systems here is the convolution of their respective impulse responses. So A convolved with the impulse response describing the element, and then with the one from the channel from the element to the receiver. So this is our end-to-end impulse response. And the black ones here are the conventional channel models, can be applied to them, any impulse response that are describing communication channel. Well, the important thing here is that the ones in the middle here that are describing what is going on within the surface, these are the ones that we can control, and I have written theta n here, or theta 1 to theta capital N, are our control variables that can be utilized in order to change the behaviors of the surface. So what can we do within the surface? Well, here is a description, a prototype for the 5.8 GHz band. It contains 20 rows with elements and 55 columns with elements, so there's over 1,000 elements here in total. And it's described in this paper of us. And each element here can be viewed as a patch, with a bias voltage V that we can control, having a reflection coefficient that is determined by properties. So Z0 here is the impedance of the surrounding air, and ZNV here is the impedance of a particular element for a particular bias voltage that we can control. And the surface looks like this. It contains some dielectric substrates and varioc diodes, and the important thing is not exactly how we build it. One can build it in many different ways using different type of materials, metamaterials, and various kind of materials in general. The important thing is what really can happen when we are controlling this element, in this case by changing this bias voltage. So here is the phase response of the reflection coefficient for different carrier frequencies. And we are zooming in at 5.8 GHz, that is where we would like to communicate in a small bandwidth. But we can see that if we have a 0 volt bias voltage, we get the black curve here. And for 4 watt we get the red curve, 7 volt we get the blue curve, and then it goes on like this. And there is all kind of variations here in phase response in degrees, from something close to minus 180 degrees to plus 180 degrees, or more than that. And by changing the bias voltage, we get variations between these things. And the important thing is what goes on in the band of interest to us, namely here. And we can see that with some voltages we can get something down at maybe minus 110 degrees. And in other values we can get plus 120 degrees. And we can choose a set of different bias voltages to create different phase responses here that we will like. We can essentially control it by just tuning the bias voltage up and down here and get any value that we will like in this range. And as we are changing the bias voltage, there is also some minor variations in the amplitude response between maybe 0.75 up to, I don't know, 0.95. There is a few tenths of a percent variations here, but in this tutorial I will treat this as a constant to keep the presentation simple, even if in reality there are some variations, and instead focus on the big variations in phase response that we can create by controlling bias voltages like this. So this is how we are actually creating our filtering within the surface. And there's definitely something that is frequency selective, but if you zoom in at this small area here, we can view it as having a constant amplitude and a constant phase value, and that is what we will utilize. Okay, so to put the pieces together and get the system model, we need to determine how we are transmitting data. And the way of transmitting data is typically to use what is known as pulse amplitude modulation, where we have a discrete sequence, x of m, where m is an integer value, that we are creating a continuous time signal based on. And we do that by taking x of m multiplied with the pulse form, p, and it's a pulse form called p of t that we are delaying in different ways. So to transmit signal m, we are transmitting p of t minus m divided by b, which is the bandwidth. The pulse form can be selected in different ways, but it should be selected according to what is known as the Nyquist criterion. So p of 0 is non-zero, but at any other integer m divided with the bandwidth, we get a value that is 0. Why is that of interest? Well, let's consider what happens with our signals here. If x of m for m is equal to 0 is 1, then what we should transmit at time 0 is a 1 multiplied with the pulse. And say the pulse is a red curve here, well then we are getting that signal multiplied with 1. Then at time 1 we should transmit the same pulse multiplied with 2, because x of 1 is 2. So we are delaying the pulse and then we're transmitting it. And then at time 2 x is equal to minus 1. We take the same pulse, but we flip it upside down since we have a minus 1. We get the green curve here, and it's also delayed in time. And then we take the red, the blue, and the green curve, add them up, we get the black curve, and that's what we're actually transmitting. And the Nyquist criterion is making sure that if we are looking at the signal at precisely the times that are in the center of my pulses here, so at 0, at 1, and at 2, you can see that at those locations, we only have one signal. The red one is positive and the blue and green are 0. Here the blue one is positive and the red and the green are 0. And here the green one have a non-zero value and all the other ones are 0. This Nyquist criterion is enabling us to sample the received signal in a particular way to get rid of all the interference. And one particular choice is to select the sync function, which has a bandwidth scaled so that it has unit energy and it has this kind of property. And the benefit is particularly that if you take a received signal, which is equal to the transmitter signal here, so if we just ignore the channel for the moment, and then we are sampling at time k divided by b for some integer k, then we are placing t here with k minus b. We get this term here, k minus m divided by b. And if k minus m, it's going to be an integer. If it's a non-zero integer, so k and m are different, then the Nyquist criterion says that the pulse will be 0. So then the term goes away. It's only when k and m are equal that we are getting something that is non-zero here. And then if we assume that it's equal to 1 in that case, then we get x of k only here. So this is how we are utilizing pulses to transmit one signal at a time, but we are designing the pulses in such a way that we can get rid of the interference between the different symbols. We're transmitting them at overlapping times, but we are sampling to get rid of the overlap. So let's now put things together. We have a received signal y of t, which is a convolution between a transmitted signal and an impulse response, and we add the Gaussian noise to it. We are selecting our filter p of t to be this sync function, and while the signal is designed to have a bandwidth of b, or b over 2 in the complex baseband, the noise is spreading out over all frequencies. And we know for sure that the signal will be confined in a particular frequency band, so there's no reason at all to have any noise in other frequency bands. So the first thing a receiver would do is to take its received signal and filter it to only consider the band of interest. And we can do that by taking the received signal y and filter it with the sync function again. We get set of t, and since y was the pulse amplitude modulator signal, we have the summation over m, we have the data symbols x of m, and previously we had the pulse from the pulse amplitude modulation. Now we convolve with the channel h, and then we convolve it with the filter p, and these two p are the same on the sign purposes here. And we have t of 1 minus m divided by b, and then we have the filter noise here. This is what we were after. Then we sample the received signal to make use of the Nyquist criterion. We take t to be equal to k divided by b, where k is an integer. We replace t with k divided by b everywhere, and we get this type of expression. We call the received signal here set of k with block parentheses here in order to say that this is a discrete signal sequence. And this looks like a pulse amplitude modulated signal, but the pulse is not p. The effective pulse is p convolved with the channel's impulse response convolved with p again. And here we had the filtered noise, and one can show that this will be complex Gaussian if w was a Gaussian process from the beginning, and have a variance that we would call n naught. And now, depending on how the channel is behaving compared to the bandwidth, then it might have an impact here or not. We might have multiple different copies of the signal because channels are in general not satisfying the Nyquist criterion. But I will only consider what is known as narrowband channels, which are narrow enough in the bandwidth of interest so that h can be written as a constant multiplied with a delta function with a certain delay, tau. In that case, the Nyquist criterion is still satisfied because we still get only p here left, and the received signal will be set of k equal to a constant multiplied with the transmitted signal plus Gaussian noise. So this is how we're developing the symbol sample complex Gaussian model in the narrow band. So let's now put all the pieces together. So we're getting our narrowband channel model when we have a reconfigurable intelligent surface. Well, the direct channel, we can describe it as having an amplitude loss and delay, as we said before, for modeling channels. Say that there's only one path like this. Then when we are moving it from the passband to the baseband, we use the same thing, we just need to multiply with e to the power minus j2 pi fct. For the channel related to element n, we had alpha n, and the square root, this is the amplitude loss determined by the channel from the transmitter to the surface. And there's delay, tau na, that we're having. And in the complex baseband, we get the same expression, we just multiply with e to the power minus j2 pi fct again, and fc is still the carrier frequency. Within the surface, we assume that what can happen is that we have an amplitude loss, which is a constant, multiplied with delta of t minus a time delay. And this is the delay that we can control by our control variable theta n. We move it down to the complex baseband, we get the same expression, but multiply with e to the power minus j2 pi fct. And we have then for the signal or the channel from an element to the receiver, b is the impulse response of the channel, beta n is describing the path loss, square root of it is an amplitude loss, and here we have the delay. We move it to the complex baseband, and we have e to the power minus j2 pi fct as an extra term. Okay, and when we are now taking a end-to-end discrete time system model, we will just get this terms here. The only thing that will happen is that we will, due to the delta functions here, replace t with the value where t minus the element that is written here becomes 0. So here we get square root of rho, and then multiply with e to the power minus j2 pi fc, and then we get tau d, the value from here. And the same thing happens for all of the other elements. So for each of our n paths, we have 3 different amplitude losses: alpha n, gamma n, beta n with square root. We are writing them together here as a joint amplitude loss. And then we have e to the power minus j2 pi fc, and then we have different delays: tau na, tau theta n, tau nb. We add those delays up, and here we have a joint delay. And here we have one of the terms that is tunable in our surface by changing the bias voltage. So this is what happens with the channel, and the transmitted signal is multiplied with this complex value, and then we add noise to it. That is our system model. We will now utilize the system model in order to optimize the communication performance, in particular select how the reconfigurable intelligent surface should be configured in order to get good performance. So we will first neglect the direct path to keep the model simple and get some insights, and then we will add it back later. So without the direct path, we are transmitting some kind of signal. It gets multiplied with this summation here over the n paths from the RS. And then we get the received signal y, which also contains noise. And our task will be to try to configure the surface so that its beamforms the signal towards the receiver. And the signal processing problem that is showing up here is that how do we get good communication performance? Well, we should have a strong signal to noise ratio, SNR. And then it's the term in front of the signal here that we can select. So that is the term that we would like to make as large as possible. And large as possible here means that the absolute value square of it should be as large as possible. And what we are summing up is n different terms. Each of them have an amplitude here, and then it has a complex phase. And when we're adding up things with different complex phases, they can either reinforce each other when they have the same phase, or they can partially cancel out each other when they have different phases. I mean, in the worst case, we have some positive numbers and we have some negative numbers. When we add them up, they're canceling out each other. You can prove mathematically, using the Cauchy-Schwarz inequality, that you get the maximum number here when all of the terms have the same phase. All of them are added on top of each other, which makes rather good sense. And that happens then when the summation over the different delays here becomes equal to a constant value. In that case, we have the same phase here for all the terms. We can remove it because we have an absolute value square, and what remains is a summation over all of the elements, and then we only have the amplitude losses like this. How can we achieve something like this, they all being equal to a constant? Well, we cannot create negative delays, so what we need to do is to rearrange a term like this and make sure that we are selecting different tau theta n that are positive so that we still get the constant value. The way that one could do that is to figure out if we put tau theta n equal to 0, we have different values, tau na plus tau nb for different elements. We are going through all the elements and we pick the largest number. This is the largest number of delay that we are getting without involving the RS, if it has 0 delay. And then we will like to make sure that all of the elements have exactly the same delay. And this is not delay that happens just any direction. It's delay that the paths will get at the desired receiver location. So we take the maximum delay, then we subtract the delay that we get for the nth path, and the difference between them is the additional delay that we need to synthetically create with our selection of the impedance. And that is then how we get the minimum positive delay solution to the problem. And suppose that we have the same alpha, beta, gamma value for all of the elements, which could make good sense. We have large distances to the surface and from the surface, so if they all are the same for all the elements, then we can remove the subscript. Then we have the summation over equal valued numbers here. We have n of them, we get n multiplied with that number, and then we square it. So then we get n squared times alpha times beta times gamma. So this is an interesting thing that happens, that the signal-to-noise ratio is increasing in not a linear manner, but a quadratic manner with the number of elements. So the motivation behind that, or the explanation, is that you have a surface area that is growing with number of elements, we're capturing more energy, and that gives us one linear increase with number of elements. And then as the surface gets larger, we also get a smaller beam width. We're focusing the energy more and more, and that gives us another factor n as our beam forming or array gain. And let me now give you an example of what is actually happening here. And remember the example I was giving you previously. We had a signal coming in from one direction to a flat surface and gets reflected according to Snell's law in that direction. And if the surface is infinitely large, we have a plane wave in and a plane wave out. This is normal reflection. And if we have a user here that is located in the other direction, outside the beam here, it will not be held by the surface. What we could do is to take the surface and bend it to get a curved mirror. In that case, the signal will be focused to this location because it's bended, and we can show it in the same way as I was presenting much earlier, that we take the element, we take the surface, chop it up into small elements, view them as small signals that are re-radiating the signals, and then we are computing the total length of every path coming into the surface and then reflected down here, and we'll see that they become equally long, and therefore this is where we get constructive interference at this particular location. What we can do with the reconfigurable intelligent surface is to approximate this, or synthetically synthesize this. So instead of changing the surface from being flat to bended, we are approximating this behavior by, in the surface, create extra delays, as if the signal had to move into the surface to a location deeper into the surface and then move out again and get reflected. So in this case, we have extra delays in the center and less delays at the edges. And that will then create a re-radiated signals that is mimicking what will happen with the bended surface like this, but it's done with the flat surface with special properties. So this is how we are focusing the signal at the receiver. And there's two things that happens. One is that we are changing the angle of the signal. So it's not going down here, it's going towards the user. And the second thing is that we are also pointing it not in a particular direction, but to the location where the user is. If the user is sufficiently far away, that is roughly the same thing as focusing in that direction. but it's important to notice that we are doing two things. We are focusing in a particular direction and at a particular point in that direction in general. If we add back the direct path, we have an additional path here, and then we have the contribution of the n elements, and the signal gets multiplied with this term. We add noise to it, and that gives us a received signal. And still, it's what goes into this parenthesis that we would like to maximize in absolute value square. So we take it, absolute value square here, and the maximum number is once again obtained when we have the same phase everywhere. So if we can then take away all of this e to the power of j something, we will just get the summation over the amplitude losses, like this. And when can that happen? Well, we can tune tau theta n, but we cannot tune tau d from the direct path. So what we need to do now is to align all of the paths from the surface with the path from the direct path. And we would like to achieve that tau d is equal to the sum of these ones. The problem is that generally tau d, if we have a direct path, is probably shorter than taking the detour via the surface. So typically there is no solution of this kind where tau theta n is a positive number. So what we need to do is rather to utilize the fact that e to the power minus j2 pi fc is a periodic function. So to find the minimum positive delay solution, we rearrange the expression to get tau d minus tau na minus tau nb, like this. And that is what we would like tau theta n to be. And since it's probably a negative number, we can add integers divided by fc, because if we put it in here, 2 pi fc times an integer divided by fc, we get 2 pi times an integer, and that is one full period. So in this way we can get a positive solution to the problem. Okay, let us have a look at the basic use case now, using this type of formulas. I will assume that I have a path from transmitter to the surface, which I call alpha, so it's not dependent on the integer or the index of the element is the same for all the elements. And within the surface, I also have the same amplitude loss is equal to 1, so there is no loss at all. And then from the surface to the receiver, I have beta as the power loss from every element to the receiver. And I have attenuation through this direct path, which I call rho. Then the spectral efficiency in bits per second hertz that I can transmit is log 2 or 1 plus the signal to noise ratio. And remember, this was the expression for the signal to noise ratio when I have tuned my surface perfectly. And in this case, gamma n is equal to 1, and alpha n is equal to alpha, and beta n is equal to beta. So there is no n subscript that is mattering here. So I can just replace the sum with the n. So I have a summation of the square root of rho from the direct path plus n times the square root of alpha times beta. And what is interesting to notice here is that alpha times beta, these are two path loss numbers that we are multiplying together. And that typically becomes a very small number. So if you have minus 70 decibels here and then another minus 70 decibels, you multiply them together, that becomes minus 140 decibels in dB scale. So for every element, you typically have a very small number. We need to have a large n here in order for the surface to actually contribute in any useful manner. So if n is small, this is probably equal to just having the direct path. We square it and we get rho. While if n is large, so that this term is dominating over the direct path, we can remove the direct path and we get n squared times alpha times beta for large n. So then for large n, we have a squaring effect that the SNR grows with the square of number element, while at small n, the surface will not make any big difference. And this is something that we can see in this example here. I have a transmitter and a receiver, and the direct path is either minus 110 decibels or minus 80 decibels. So I'm considering these two different cases to demonstrate how strong the direct path is compared to the other path. And then from transmitter to the RS, I have minus 80 decibels, and from RS to receiver, I have minus 60 decibels. So that is a rather good channel, actually. Even if the path losses numbers seems to be very small, what we can see is that even over just a few meters distance, this is a good number. So we can say that the receiver is rather close to the surface, while the transmitter have been placed together with the RS to have a good channel here. And then we have either a good channel in case 2 or a fairly bad channel in case 1. I consider a bandwidth of 1 MHz. And the transmit SNR, so if I take the transmit power divided with the noise power that is on the receiver, I get 100 decibels. And then this should be multiplied with a different path losses here to get the actual SNR. Here I'm showing you the capacity in megabits per second as I'm changing the number of elements. Starting from 0, this is what I get without an RS. In case 1, I get the number close to 0, so that is because I have a bad direct channel. If I instead have case 2, so I have a rather good direct channel, I'm starting at a rather high number here. So since I have 1 megahertz, this is like 7 bits per second in hertz. And as I'm then adding the elements to it, you can see that if I'm starting in case 1 where the direct path is weak, we are quickly seeing an increase in the capacity. And here we are observing this kind of squaring effect that it grows quickly with the number of elements. While if I'm at case 2, we see a benefit from adding elements to the surface, but the benefit is not making as big difference because they already had a strong path. So we will need to have rather many elements before the extra energy that comes from the RS path will make a big difference in terms of performance. So the solid lines here, the red one and that I have up here, and the blue dash dotted line down here, this is when I can select every element to have exactly the configuration, this phase that I would like it to have. The black curves that are underneath them is when I'm restricting myself to select only 1 out of 4 different configurations. So I can have minus 90 degrees, 0, plus 90 degrees, and plus 180 degrees, or at least they are 90 degrees separate from each other. That is the only thing that is important. And we can see that the difference in performance is actually rather small. Why is that? Well, if we are adding up many paths, each of them can have a random any phase in the complex plane. Then with just 4 configuration, we can move all of these contributions into the same quarter of the complex plane, which means that they will be pointing in roughly the same direction. So we are only losing like 1 dB or something like that in center noise ratio by having only 4 configurations. So even if it's totally physically possible to change the bias voltage continuously and achieve any configuration that we will like, probably it's enough to find 4 different values on the bias voltage that gives us 4 different configurations. Well, one can even get away with only 2 different options. The point with this simulation example is that the reconfigurable intelligent surface can improve the capacity vastly, but it's particularly happening when the direct path is poor. So we should deploy these surfaces to deal with situations when we have a bad channel to start with in order to improve the coverage. Here is an experimental validation that it actually works in reality and not only in theory. So this is in a paper with my colleagues in China. So they placed at 50 meters distance a transmitter with a horn antenna directed towards a copper plate here, and they are transmitting. They are using that surface I was describing earlier, and it's a 5.8 gigahertz band. They have 20 megahertz of bandwidth, 13 dBm power, and they're transmitting the signal towards this direction. There is a copper plate here as a baseline that is reflecting the signal, probably according to Snell's law. We have a receive antenna over here. It's also a horn antenna, so it's 2 rather directed antennas towards the surface here. And you have a USRP that is processing everything, and we have that at the transmitter as well. And when you have a copper plate here, the signal gets reflected And if we look at the received signal over different frequencies, this is the band, the 20 megahertz, where the signal is supposed to be. And we see small variations outside its band. This is the noise. And within the band, you can see that it's above the noise floor, but it's no big variations. The maximum number here is around minus 66 dBm. If we replace the copper plate with this reconfigurable intelligent surface that I was describing earlier with 1,000 elements, we can configure it so that it reflects the signal towards this receive antenna instead of just in a way determined by Snell's law. And then we can all of a sudden see a much stronger signal within the desired band. We go from minus 66 to minus 39 dBm. So there is really more than a 20 dB, rather 27 dB improvement here. So it really shows that the surface is able to reconfigure itself to reflect signal energy into this horn antenna. I will show more example of how we can utilize reconfigurable intelligent surfaces later in this tutorial, but before that we will cover the second topic, namely holographic massive MIMO, and then we will jointly look at their channel models and their performance later on. So a massive MIMO system of today is a 5G system operating in 3.5 GHz band, might contain 64 antenna integrated radios, and have a 1 meter times half a meter sized array that we put on the rooftop. And we can utilize it to direct signals towards different users to get array gains, so focus signal energy towards them, and the spatial multiplexing gain of transmitting many layers of data at the same time to different users using the same frequency. But even if we call it massive, it's not particularly massive. So if you zoom out the picture here, what you can see is that each of these panels here that you put on the rooftop, which is a massive MIMO base station, they contain many elements, so it's a large number in terms of that, but they are electrically small. If you view them as a user from a distance, they are far away from you, and therefore they are creating a beam in your angle directions, but they look small from distance, so not filling up your field of view. What I would call holographic MIMO is a physically large array that contains even more elements, but the important thing is they're electrically large. They are filling up a much larger part of the field of view. And that is something that can be utilized for making use of phenomena that are normally not present or not something that have an important impact on our performance. The general vision is something that was showing up under the name large intelligent surfaces. And this is from a paper here from colleagues at Lund University. Beyond massive MIMO, the potential of data transmission with large intelligent surfaces. And their idea was to take surrounding surfaces that we have in our everyday life and turn them into intelligent walls in the way that this user here can get signals transmitted to itself from one part of the wall, this device here from another part of the wall, this user from a third part of the wall. And this can be done both outdoor and indoor, for example. And this can not only be used for data transmission, but also for positioning users and for sensing purposes to see what happens with radio waves in this room, is people moving around and so on. And in this tutorial, I will focus only on the data transmission part. And the main thing is that when you are close to the surfaces and they're physically large, we have a high spatial resolution. We can measure things in space in a much more high precision way, which requires us to have new propagation models to understand what happens in the near field of arrays and to consider realistic scattering conditions. So let's start with talking about the near field and far field of an antenna. And this is an old topic that is often considered when we are analyzing antennas. So if a transmitter is sending out the signal, it sends out the spherical wave that is propagating in all directions or in selected directions, and it has a waveform here that is spherical. So when we have a plane receive antenna at a distance d, then the distance to the center and the distance to the edge will be different. If you have a distance d to the center and distance d prime to the edge here, then since the you have spherical wavefronts, the signal will reach the center before the edge. And this is something that can be analyzed, and the length difference in particular, if you take d prime minus d, and we can then write d prime as the total distance d here to the surface, and then if you have a length of the antenna which is a, then this half here is a over 2, and d prime will then be d squared plus a divided by 2 squared, and take the square root of that. That is some trigonometry. And then we should subtract d again. And this is the exact expression for d prime. If we are making a small difference or small a approximation using a Taylor approximation, then this whole thing will become a squared divided by 8d. And this is then the length difference. And when you have radio waves that are propagating like this, the thing is that the difference in distance here will determine what is the phase shift between the signal received at the center and at the edge. And this extra wave, extra path here, which is d prime minus d, will create an additional phase shift. So we might have a blue signal and a red signal that are received at the edge and at the center. And what is often assumed is that we would like this phase shift to be smaller than pi over 8. And this is just an arbitrary selected number, but if that is the case, if pi over 8 should be greater or equal to the actual phase shift that we're having, we take the length difference, we multiply it with 2 pi divided by lambda, which is sort of determining how much of a period that we are getting over this extra distance. It depends on the wavelength lambda. Then we can rearrange in the expression, and we will get that the distance should be larger or equal to 2 times a squared divided by lambda. In that case, we will get a phase difference that is smaller than pi over 8. And in those cases, we can probably neglect that we have a spherical wavefront and view it as if the difference is so small so that everything that is received over the antenna is in phase. This is known as the Fraunhofer distance, and if we are and it's often characterizing where we have the near field in propagations when it comes to an antenna. So if we are at longer distances than the Fraunhofer distance, we need to we can ignore that we have spherical wavefronts and the phase differences over the antenna. And if we are at shorter distances, then we need to care about those effects. And there are also other electromagnetic effects that are appearing. There are evanescent waves. There are magnetic inductions, which is, for example, utilized in order to charge different devices, and which are used in RFID, for example. But in general, if we are computing the distances to an antenna, we are much further away than the Fraunhofer distance. But if we are applying the same concept to arrays, then we might not be that. So if we have a transmitter that is sending out the signals, we have our bended waves here, spherical wavefronts, we have antennas of size A, and then we have many of them, so the total aperture here is B. Then practical operating regime is typically that we are in the far field of each antenna. So the distance to the array here is a d, which is much larger than 2 times a squared divided by lambda. So this is the Fraunhofer distance applied for every single element. But if you apply the Fraunhofer distance instead for the entire array here of b, we get 2b squared divided by lambda. And we can be in the near field of the array if the distance d is smaller than this number. To give you some example, say that we are at a 3 GHz carrier frequency, where the wavelength is 0.1 meter, and we have an array which is 10 wavelength long, which is 1 meter. In that case, we have a Fraunhofer distance for the entire array, which is 20 meters, and we can possibly be that close to the array. If we are having a surface which is 100 wavelength wide, which is 10 meters, then if you put it in here, since we have a square, it's increasing quickly, so we get 2 kilometers. So in this case, we can actually put up a 10-meter large array, and people who are up to 2 kilometers, typically everyone who is served by this base station with this big array, will be within the near field, within the Fraunhofer distance. So what does this mean for communication phenomena? Well, in the near field, we have spherical waves that we can actually measure over, not the individual elements because we are in the far field of them, but over the different antennas. So let me give you an example. We are at the 3 GHz band, same as before. We have 200 antennas, and we have a lambda over 2 spacing between the antennas. So in this case, if we have many antennas, then since we have 200 of them, we can get an array gain of equal to 200 when we are processing our signal. And what I am showing you here is that if we operate in the system, taking into account that we have spherical wavefronts, so that we cannot just compute the distance to the location D here, but we need to consider the distance to every single element in order to figure out how we should delay our signal when we're transmitting and how we should sort of rotate the received signal in order to add them up constructively. In that case, irrespective of what distance I'm in, from 1 meter up to 2,000 meters, the blue curve here is showing you that we can get an array gain up to 200, and at least until we are very close to the array. If we are instead pretending as if we are in the far field of array, we are using far field approximations like array response vectors in order to figure out how we should phase shift different antenna elements, signals, in order to get the array gain, then at 2 kilometers, that is our Fraunhofer distance in this case. And at that case, there starts to be a difference between using the exact phase shifts and believing that we are in the far field. So we see a separation, and when we are down at 1,000 meters, there is a loss in array gain by maybe 20%, and when we get even closer, there is a huge loss in array gain. So what is it that is happening here? Well, the array response of the array here for a signal from this user depends both on the distance to the user, to the center of the array, and on the actual angle that it's having. So we need to take both of those two factors into account when building our system effectively. And there's also some additional phenomena that is appearing here, which I will return to. So what is happening when we can see the spherical wavefronts is that we get a depth perception. So that is something that you can notice yourself when you have two eyes. So if you hold your hand over one eye, you can really measure the depth to different objects. But by having two different eyes, which are slightly different from each other, you're able to tell how far away different objects are based on these two different measurements. And it's essentially the same thing that can happen when you have multiple antennas and the array is sufficiently large so that you are able to measure the spherical wavefronts, and in that way you can measure how far away the user is as well. So consider two users that are in the same direction, and we consider the same array as before. And we are putting one at a fixed location and one at a varying distance d, from 1 meter up to 2,000 meters. And in the first case here, I have put one user at 1,500 meters distance. And I'm computing the channel vector to that user, and then I'm computing the channel vector to users at other distances, and I compute the normalized inner product to figure out how similar the channels are. And if both users are far away, we are essentially in the far field, or approximately so. Remember, the Fraunhofer distance is something that is arbitrarily selected. So if I'm put one user at 1,500 meters, and if I'm between 1,000 meters or further away than that, then both of the users will have essentially the same channel vector apart from a scaling factor. So that is what we are typically used to having. Two users located in the same direction, we cannot tell them apart based on the distance. but only based on angles. If they have the same angle, they have the same channel. And however, if the user that we are moving around is closer, so if it's just a few hundred meters away, well, then we actually get different channel vectors thanks to our depth perception. And we can see the effect even more clearly if we have one user at 50 meters and then we're moving around that user. So we have one user that is fairly close to our array. In that case, if the other user is also at 50 meters, then they have the same channel. But as soon as you move just a few 10 meters away from the user, we will have a large drop in a product between these channel vectors. And that is then resulting in the fact that, well, we can see the difference between the users even if they are in the same angle because they are at different distances. And that ability to do that is better the closer we are to the array. And here is another way of illustrating that, namely something I call near field focusing. And this is focus in particular what happens when you're really close to the array. So say that we have an array here which is 5 wavelengths wide, and we put the user 5 wavelengths away from it. And then we're focusing the signal energy at that location, and I'm computing the array gain that we get at various locations around. So here's the location where I would like to get a strong signal, and we get a strong signal at that location, represented by a large number here. And then at other locations, well, the array gain is dropping very quickly around it. So the signal is only strong in the small spherical region around where the user is, and it has a radius of approximately 1/4 of a wavelength. So in this case, we're actually focusing the signal not only in a direction, but on a point in that direction, a point that is nearby. If I am then computing what is the Fraunhofer distance in this case, well, my array is 5 lambda wide. So I put it into the formula, and 50 lambda, that is our Fraunhofer distance. And here I'm only at 10% of that. So then we see this focusing effect. If I am increasing the distance to 10 lambda, well, in that case, I'm focusing the signal here. I get the maximum array gain here. But you can see that behind the user, there is still quite some signal focusing. So we are actually focusing a beam. It's not entirely the same. We would get the same array gain all the way here if we are at the Fraunhofer distance or further away, but they still are creating a beam in a particular direction. So the Fraunhofer distance is not providing us with a clear cut between above it we get certain effects, and at shorter distances we get other effects, which should be particularly close. And when we get the most interesting effects is when the distance to the array is roughly the same as the width of the array, and we will return to that. Okay, so now I talked about the effects that can happen when you have large arrays. Why are we talking about holographic massive MIMO in that cases? Well, one thing might be that holography is a way of generating signals where we can see the depth. But more importantly, one can view it like this. The way of recording holography is that we illuminate an object with a wave, and then that wave gets reflected, and we are recording it together with the reference wave that we are generating. And then we can let this recording medium generate the signal that was reaching it. And the way of doing that is to take the same medium as a display and send the same reference wave, a replica of it, through the surface, and then it will radiate a reconstructed wave as if it was the original reflected wave like this, and therefore it creates a virtual image like this. And this is essentially a way of building these large arrays. And we can view this as being a signal that is transmitted. This is the propagation environment. We get the received signal here. And then if we would like to transmit back, we do the opposite. And nowadays, you can create holography using meta surfaces. Surfaces are metamaterial, similar to the way we can build reconfigurable intelligent surfaces. So in that case, you have a light source, you have a meta surface that the signal is propagating through, and then we are generating different holograms on the other side of the surface. So if a reconfigurable intelligent surface is something where the signal comes in from one side and gets reflected on the same side of the surface. We can create large active surfaces by having a meta surface where we are generating a signal at the back side of it, and then it goes through the surface, it gets phase shifted by a meta surface material, and then we get to re-radiate the signal. So this is what is started to be called holographic beamforming. So it's a meta surface with the built-in source RF generator at the backside. There is no path loss between this generator and the surface, which is a good thing. And this is a large difference from the reconfigurable intelligent surfaces that we talked about earlier, where you can also use metamaterials, but then we put the surface at a very different location than the transmitter or the receiver, and therefore there is losses between them. So this is one way that one can potentially build large surfaces using metamaterials, and it can have a thin form factor with the idea that it should be invisible to deploy, and ideally the surface is a contiguous surface, but in reality we are approximating it with having small elements with varying impedance values so that the signal gets delayed in different ways. And the name holographic beamforming has even been trademarked by a company called Pivotal Comware, who are building small holographic beamforming solutions. So this is their millimeter wave solution for the 28 GHz band. It's a small array, it only has one RF chain at the back side of it, and it's not much larger than a quarter. So it's not at all the large surfaces that we have in mind with multiple RF generators at the backside, but it's the first step towards actually building this type of things. So the whole idea of using meta surfaces in order to build transceivers or build communication systems is something that is already commercialized when it comes to building transmitters or receivers, using it for radar applications or satellite receivers, but when it comes to reconfigurable intelligent surfaces, we are further away from commercial utilization. So we can build something like this. And why are we talking about building a contiguous surface? Well, what happens when we are shrinking down the antenna spacing is that we get a signal transmitted that is cleaner. So what one can see here is that I am looking at the beamforming gain in a particular direction. So I'm beamforming towards 0 degrees. And then I'm considering a surface with a fixed length and fixed height. So this is sort of a panel, square panel. And I am considering different antenna spacings in different areas. So I have a distance between the element which is 0.75 lambda, 0.5 lambda and a quarter wavelength, and then the expression that I get when the antenna spacing goes towards 0. And what one can see is that the main beam is only determined by the aperture of the ray, which is typical in wireless communications. So it's only the length and height that is determining it. But as we are making the element smaller and smaller, we are getting smaller side lobes here on the side. So this is one reason to shrink down the element sizes. Of course, there are other electromagnetic effects that one have to take into account when building these type of things as well. Here we are neglecting mutual coupling, for example. But we shouldn't do it in order to try to shrink down the beam width. Then it's better to spread out the antennas. But we can get side lobes that are smaller, for example. So I would say the main reason to actually consider having small antenna elements is that in the limit, when you have a contiguous surface, we are getting integrals instead of summations over the different elements. So that makes it easier to analyze the communication performance. Okay, an interesting thing when we are building big surfaces that are contiguous is that we can consider how many signals to different users or the same users can we multiplex at the same time. How many users can we separate? And in order to answer that question, it is incredibly important to have propagation models for the channels that are physically meaningful. You cannot just cook up any model. It might be fine in order to predict the performance for small systems, but when we are considering large antenna arrays, we need to make sure that we are satisfying the Helmholtz equations and modeling of the practical scattering environments that actually exist is going into the model. Otherwise, we can have huge mismatches when we have large surfaces, while the mismatch will only be tiny when we have small surfaces for our antenna arrays. So one can go into much detail and analyze what happens when you have a surface or receiving volume. There are different scattering objects around it, and if there is a lot of scattering around, how many different signals can this array separate? And I will not go into the exact details, but only the results and what can obtain from that. But I think a key thing to remember is that the independent Rayleigh fading or ID Rayleigh fading model that has been very popular to use to study small arrays should never ever be utilized to study large arrays, because they are not physically meaningful. They cannot appear in reality, and we will come back to some issues around that later as well. Let's now define something called a spatial degrees of freedom. And degrees of freedom is something that is often appearing in capacity analysis when we are saying that the sum capacity behaves as eta times log 2 of the SNR plus a constant at high SNR. If that is the case for some value eta, well then eta is called the spatial degrees of freedom, and it describes how many different streams of data that we can spatially multiplex. So if you only have one stream of data, we will have something like log 2 of 1 plus SNR, which at high SNR is like log 2 of SNR. And if we can multiplex many of them, we get the factor eta in front of it. So how large is that number eta? Well, that can be characterized, and there is a good paper, Spatial Stationary Model for Holographic MIMO, small-scale fading, that is characterizing this in the ideal cases with a lot of fading, a lot of scattering. If you have a one-dimensional array, uniform linear array of length L, then what we will get is eta is equal to the length multiplied with 2 over lambda. And this is closely connected to sampling of signals. So when we are sampling a time signal, we are sampling it twice per period, or we take the bandwidth and we sample twice times the bandwidth. And here's the same type of thing. When the signal is propagating over space, we should sample it twice per period. So this 2 divided by lambda is representing that. So just as sampling of band-limited signals is determining how often we should sample in order to extract information uniquely from it, we can also consider space-limited signal. How quickly can the signal vary over space? Well, that is determined by the wavelength. And in 2 dimensions, if we have a 2-dimensional array, which is what holographic MIMO is really about, and essentially all types of antenna arrays that are used in reality nowadays are also 2-dimensional, then if we have a length L and a height h, one might expect that we will get L times h, and we do that, then multiply with 2 times lambda and square that as well. But that is not what we are getting. Instead, we get pi divided by lambda squared times L times h. So if this is our received aperture, then we have a length and we have a height, and we have a lot of different elements here. And it's actually only the elements that are within a circular or spherical, or rather cylindrical area here, ellipsoid in the middle here, that is contributing to the degrees of freedom, while what we have at the outside here is only receiving the same signal as the ones at the inside. So one can essentially remove these surfaces elements outside and not reduce the degrees of freedom. Then these ones can still contribute to a bigger constant here, but not to degrees of freedom. So this is a formula that can be utilized in order to figure out how many signals can be spatially multiplexed ideally. So let me give you an example of that. So we have massive MIMO arrays, and we have a holographic MIMO array on the entire facade here. And we have the 3 GHz frequency, as I'm usually considering, because that is the main 5G frequency. And what we have at the 5G massive MIMO antenna panel is 64 antennas, which means that we can at most spatially multiply 64 streams. And typically it's rather built for 16, for example. If we take a holographic MIMO array here, or also known as large intelligent surface, it's 10 meters long and 30 meters wide. We put it on the entire facade of the building. We put it in here we get L times H, so that's 300. Then we multiply with lambda, with pi, and then we divide with lambda square, which is 0.1 in this case. Well, in this case, we will get approximately 100,000. So there is a huge difference between 100,000 and 64. So we are very far from these limits. We can definitely put up a big surface with antennas on the facade of a building and serve a huge number of users. What will really limit us in reality is the number of users that are there and potentially the richness of the propagation environment, because you need the signals to come in from sufficiently different directions so that we can separate them. We were seeing earlier that we get this depth resolution, but it's even better if the signal comes in from different angles, or if there are multiple paths that we can utilize them to separate the signals even more. So this brings us into a very important topic of spatial channel models. We need to have channel models that are appropriate when considering arrays that are large, and that applies both to holographic massive MIMO and to reconfigurable intelligent surfaces. So let us start with the far field. And for a typical array like this, plain array with many elements, we have horizontally NH different columns like this, from 1 up to NH, and vertically in each column we have 1 to NV, which is the vertical number. And when studying a plain array like this, it's usually useful to consider spherical coordinates. So in the XY plane here that we have at the bottom, we are defining the azimuth angle, phi, and we can change it from minus pi to pi, so that's like moving around the equator. And then we can move up and down using the elevation angle, which is starting at 0 right in front of the array, and we can go up and we can go down, so that's like moving up towards the poles on a sphere like the globe. And then a multipath component can arrive to this array or leave the array in one pair of angles here. A azimuth angle, 0 degree is straight in front of it, and then we can move around, and different elevation angles. So if you consider a certain element here at location UN, and this is three-dimensional, so it has 3 different coordinates, and since it's located in the Y set plane, the X component will be 0. Then we can compute what is known as the array response vector. It's a vector of length equal to the number of elements, and we can order the elements in any manner we like. And the way of computing the signal phase shift at a particular location here is to take its location and take an inner product with something known as the wave vector, which is determined by 2 pi divided by lambda. And then we have this transformation here that comes from how we transform XYZ coordinates to spherical coordinates. So by taking this inner product, multiply it with the complex number j, or imaginary number, and take the e to the power of that, we get a different phase shift at different elements. And this is what we can do in order to consider when we have one plane wave that is impinging on the surface. Then the received signal will be that plane wave multiplied with the constant and the array response. That's sort of the different channels to different elements here. Based on that principle, we can create channel models. So say that we have waves coming in from different angles. So here we have phi 1, theta 1, phi 2, theta 2, phi 3, theta 3. We have n elements, each of them have an area A. Then the channel vector for the entire array can be written as the summation over our L different plane waves that are impinging. For each one of them, we are taking the array response vector for the corresponding set of angles, and then we multiply it with a constant, which here I will write it as a constant divided with square root of L, and then I sum up with number of elements L here. In reality, there's of course a constant here determined by the scattering object that gave rise to this impinging wave, but we will have this one in order to consider what happens in multipath channels when we have many elements. Because one can model the system when L is large using what is known as Rayleigh fading. And if you remember, I was a bit critical against independent and identical or IID Rayleigh fading before, and I'm still is. But there is other types of Rayleigh fading, namely when you have correlated fading. And then you have a channel vector, which is complex Gaussian distributed, circular symmetric complex Gaussian distributed. It has zero mean, as any circular symmetric distribution has, and then it has a covariance matrix. So if you have n elements, this is an n by n matrix that is describing how correlated the signals will be at the different elements here when you're comparing two different elements. And we can achieve Rayleigh fading from a model like this as the number of plane waves that are impinging go into infinity, and in order for the energy to stay constant, or at least finite, we need to have just both a summation over L, and we need to have a factor here that's normalizing away the energy. So assume that these CL terms are independent and identically distributed. They have zero mean and a variance, A, which is the area here, and mu, which is describing sort of the average energy per area unit. Then these are describing both the amplitude losses and some kind of phase shift that the entire wave have when it impings. Then we assume that the wave is coming in from an IID angles from a certain probability density function, or PDF F. Then we can compute the covariance matrix for these signals by taking, for every element, we take the corresponding element from here, we take the location that this element have, we take the nth element and the mth element, they have un as their location, from their location, and both of them had as their phase shifts in A, that you took its location, we took the inner product with the wave vector, and now if we take two of them, we take their product, we are getting this expression like this. And what we should do is to take an expected value over this, but over the variations of the angles here. And we have already computed the averaging over C, and that is resulting in this result here. So as L goes to infinity, H, the channel here, will in probability converge to a Gaussian distribution with this covariance matrix. And you can, for any probability density function of the angles here, compute what R is going to be. Let's consider the sort of most extreme case, where scattering comes from all directions. And since this is a two-dimensional array, it cannot really come from the backside. So let's assume that we have a uniform distribution in one half space in front of the array. And if I'm then considering the azimuth angle here, then 0 degree is right in front, minus pi over 2 is to one side, plus pi over 2 is to one side. So my probability density function will be defined from minus pi over 2 to plus pi over 2. And then I can have any elevation angles going up and going down. And that's why I don't define it like this. But when this isn't true, it should be 0. And I get cosine or theta, that is something that comes from the behavior when I have a uniform distribution over a sphere. And 2 pi here is normalizing, so if I integrate over the entire sphere, I get 1. So we have probability density. If we put this into this expression, the expectation here, and compute it based on this, one can show that, and we do this in this paper here, Rayleigh fading modeling and channel hardening for reconfigurable intelligent surfaces, that the expected value here turns into a sinc function of 2 divided by the wavelength lambda, and then you have the distance between the two elements within the array. So this is the Euclidean distance between the two elements. And this is something that you might have been familiar with from before as well. It's the 3D Clark's model, where we say that when you have an isotropic fading model, if you look at 2 points, it's only when the distance between them is a half wavelength spaced, or if you have an integer times half a wavelength, that you get no correlation at all. And this is represented by the fact that the sinc function is only going to be 0 when you have a positive integer or negative integer here, not when it's 0. So the spatial correlation matrix here will contain elements computed like this. You can consider any shape of your two-dimensional array here, compute a relation or covariance matrix like this. And as long as you are in 2 dimensions, this will never ever be a scale identity. And the reason for that is that there is no way you can put up more than 3 elements. You can essentially take a equal side triangle and put out the elements there. But as long as you have more elements than that, there is no way you can put out the elements, so they always are an integer times half the wavelength spaced. For example, if you take half a wavelength horizontally, half a wavelength vertically, then all of the diagonals will have different spacing, so you will have correlation along that type of spacing. And this is essentially what gave rise to that result that we talked about earlier in terms of spatial degrees of freedom, namely that when you are having a planar array, not all the elements are actually providing you with extra degrees of freedom because of the spatial correlation. And what this in particular implies is that if you take this covariance matrix that we were just computing, you compute it numerically, you compute a rank of the matrix, so how many eigenvalues are non-zero, then you are dividing with a number that I had before, but now I have formulated in terms of we have n element, each of them have an area A, and that will then build up and L times H equal to that. Then the spatial degrees of freedom will be pi NA divided by lambda square. And when the number of elements grows large and every element becomes very small, but still the array is larger, so n times a goes to infinity, then asymptotically in that regime, the rank of the covariance matrix that I was just presenting will converge to this number here. Or since both of them are increasing with n, the ratio goes to 1. So what this really means is that approximately the rank of the covariance matrix I just presented will be equal to this number. And this is something I can illustrate here. Say that we have a 40 times 40 element array, and I have A as my area, and I will change the area of every element, but we have always 1,600 elements. Then I'm computing the covariance matrix based on the expression on the previous slide, and I'm showing you the eigenvalues of them in decreasing order, like this, from 1 up to 1,600, because that is the number element that we will have. If we would have IID Rayleigh fading, then we will get the dotted line like this. All of the eigenvalues are equal to 1. If I normalize the covariance matrix to have that trace. If I take half a wavelength spaced elements, then what will happen is that all the elements horizontally we will uncorrelate with each other if they are in the same row, and if you consider elements along the same column, they also uncorrelate with each other, but along the diagonals you have correlation. And even if you think, but that correlation shouldn't really make a big difference, it does. Because if you're computing this expression here, you have a fraction of the eigenvalues that will be exactly 0, at least asymptotically. And that is represented here, but by the fact that you have some eigenvalues that are, let's see, 1, 2, 3, 4, 5 times larger than the average. And you have some fraction of the eigenvalues that are incredibly small here towards the end. And some of them are varying. So that type of effect is there. Furthermore, I was mentioning earlier that both reconfigurable intelligent surfaces and holographic massive MIMO is based on the idea of having small elements. And if we now go down to lambda over 4 or lambda over 8, lambda over 4 I get the red curves here, so then I have much fewer eigenvalues that are non-zero, and they are also larger. And when I have even smaller element, I get this behavior here. So it's only a few ones that are 0. And by the way, the circles here are illustrating when the rank should go to 0 according to this approximation, that the rank would be equal to this number. If this was true, I will go to 0 exactly at the circular areas here. And you can see that the rank so far is slightly larger, but it's a good indication. And it's only when the number of elements goes to infinity and the element size goes to 0 that the difference should go away. And we can see that when we make the element smaller, it also becomes a more accurate approximation. So what is the point here? Well, there is channel sparsity we have n dimensions, but even if signals are coming from all dimensions, you are not utilizing all dimensions. You can never do that. And why is that? Well, there are two contributing factors. One of them is the sub-wavelength antenna spacing that is removing a lot of the dimensions. So we are oversampling a space. Why do we do that? Well, we do it because we want to be able to spread out the signal energy more. But that is not providing us with the better ability to actually send more signals, because that is determined still by the spatial degrees of freedom, but only the ability to steer signals better and get a power gain from that. And even if we have half wavelength spaced arrays, we will still have a two-dimensional surface, which is removing some of our degrees of freedom because of the spatial correlation that is inherent in that. So ideally fading will, even in that case, be a bad model. You should never ever use it for these kind of systems. One could motivate them for one-dimensional arrays, but we are not using that reality, so ideally fading is not the go-to method. And in particular for reconfigurable intelligent surfaces and for holographic massive MIMO, we should use models that are taking these smaller spacings into account. Then I'm not saying that one should use the isotropic scattering model that I was just describing, because in reality we might have even sparser channels. So if we have L different paths coming into this array, here we have the actual channel model that we could consider, where H is created by having L different plane waves. Each plane wave is characterized by two different angles and one element here that is describing the amplitude of the signal, for example. And if we have n elements here, well, we have n complex parameters in H, and that can be utilized in order to characterize the vector. But if we have a small number of L plane waves here, then for each one of them we have 3 parameters, 2 angles, and 1 complex phase here. So it should say that we have 2 real and 1 parameter times L here, that is complex. But if L is much smaller than N, or if you have one path that is much stronger than the other one, which is typically the case in line of sight channels, well, then we can probably model it as a sparse channel and say that even if it's described by n complex parameters, we will still be able to describe it by a small number of them if we can just utilize the geometry here. So geometrically accurate channel models is really key in order to analyze both of these two technologies. Let me give you an example of what would happen when it comes to reconfigurable intelligent surfaces. So in this case, we had a direct path with a amplitude loss and a phase shift. We have a summation of our n elements. Each of them have a combination of amplitude losses and phase shifts. We can write it as an inner product between two different vectors. One part that is gathering everything that has to do with the reconfigurable intelligent surface. So it's amplitude losses for each of the n elements and the corresponding parts here with the phase shift for the n elements. And then for each element, it should be multiplied with alpha n, beta n with the square root, and then e to the power minus j 2 pi fc, and then we have the sum of their two delays. And if you put that into two vectors in a similar way, and then we consider a element-wise multiplication, then we are creating each term here by taking one term representing the channel from the surface to the receiver, one from the transmitter to the RS, and one that is describing what's going on inside the RS. So we have one vector describing the RS. This is a controllable vector. We can select it. And then we have one channel describing, one channel vector describing the channel to the receiver from the RS, and one from the transmitter to the RS. Both of these vectors can be described and modeled in the way that we're just describing. They will most likely be sparse vectors using a sparse channel model based on the geometry of the array and based on what kind of propagation environment we're having, with maybe only a few dominant paths. So without sparsity, how many elements is there to learn here about the channel? Well, we have one here from the direct path, and then we have the product here of the like cascaded channel to and from the surface. So there's n element in this vector when we have taken the product, and then we have one here. So there's n plus one element. And if we have 1,000 elements, there's 1,000 different parameters to learn. But if we have sparsity in these two vectors, we might be able to utilize that. And we will return to that in a moment. What I described so far is how to model the channels for the surfaces when we are in the far field. But then I was also saying that one of the key interesting things that could happen when you have a big surface is that you can also have near field behaviors. And particularly interesting thing was happening when we were so close to the surface that we can actually focus energy in small regions and not create beams. And this is created by 3 different near field phenomena. The first thing is that even if you have one distance to the center array, the distance to the different elements in the array will be different, and we cannot approximate them as being roughly the same. And this is then affecting the path loss to the different elements. Usually, we can neglect the path loss differences and only care about phase differences between the elements, but not in the near field when we are really close. And even if each element have the same physical area, when we are viewing them from different distances, from different angles, they will view them as they have different effective areas. So if you are taking a sheet of paper and look at it from the side, it will look smaller, and it's the same type of effect. And we also have different polarization losses depending on when the signal have a particular polarization. When it's entering the array from different angles, it will also react together with the elements in different ways. And I will not go into exactly how to model this in detail, but one can compute expressions for this. So the path loss for the entire surface here is determined when you have a receiver, you have a transmitter transmitting to this array here. We would like to figure out what is the path loss, what fraction of its transmitted signal, if it have an isotropic antenna that is being received here. And if you have n elements, distance d to the center, then beta d would be a, the area of one element, divided by 4 pi d square. So that's what you would expect that the element in the middle will capture. But if you would like to compute the sum of all of those fractions for the entire surface, we cannot take this element and multiply with number of elements when we are in near field. We get this much more complicated formula instead. So I will not go into the detail, but you see that it contains the number of elements, it contains this path loss factor, but also a number of other things. If we have a large distance d, so d is much greater than the width of this, which is n, the number of element, times a with the square root, because we have square root of n elements in each dimension, and each of them have area a, then in that case one can actually show that this formula can be approximated as n times this formula, just as we are expecting it to be in the far field. While in the near field, if you let number of elements go to infinity, so you have a surface that is starting to grow in an entire universe, then eventually, of course, the elements that you put further away will contribute less and less, and one can show that the limit here is 1/3. So what is the reason for that? Well, if you have an isotropic transmit antenna here, half of the energy goes in the wrong direction, so that contributes to 1/2, and then you only get 2/3 of that, and that is because of polarization losses. Okay, so we are reaching towards the end of the tutorial, but I will consider in particular 2 of the main open problems that is related to this technology. And I think the first thing is, what are suitable use cases for technology like this? When we are developing new technologies, we shouldn't focus too much on use cases, but rather to focus on what are important performance metrics that we can care about, and then try to improve them as much as possible using new technology aspects. And then we can later see which of these aspects that are important to implement in reality based on what use case that actually becomes important in the future. So here is from the 6G flagship white paper from 2019, some of the main use case that people have been talking about, or rather performance metrics. I think that the reconfigurable intelligent surfaces and holographic MIMO is mainly about the things that I have circled here. We can improve energy efficiency by utilizing our transmission energy much more effectively, focusing the energy where it should be and not where it shouldn't be. And we can handle more devices. We can spatially multiplex them. And to some extent, we can also utilize the surfaces to mitigate fading behaviors and get more reliable physical layers. We can push peak data rates, but I think it's even more important in the future to take the lowest data rates and push them up instead. So let's go into some details and think in particular about the capacity of a wireless system. So number of bits per second that we can transmit in a certain cell area. We can write it like this. For every data stream, every layer that we're transmitting, we have the bandwidth multiplied with log 2 or 1 plus the signal power that we're transmitting, then multiply with the beamforming gain or array gain that we're getting. We have a path loss factor, and then we have the noise power spectral density, we have the bandwidth again. And then we should multiply the whole thing with the multiplexing layers that we're having in our system. There's basically 3 ways that we can improve the communication system's capacity. One is to multiplex more layers. That then means that we are sending them to one user or to multiple users. So we increase the multiplexing layers here in front of the signal, and probably need to improve the beamforming gain as well in order to deal with additional interference in that case. We can use more bandwidth, and that also needs to be associated with probably higher power and or a larger beamforming gain. So more antennas is important in that case as well, in order to be able to utilize higher bands, just to get the power through the system. And we can also, of course, reduce the range of our system, so we are getting a better path loss number. And in that case, we typically also get more interference because of the shorter ranges, and then we also need more antennas to deal with this. So more antennas goes in everywhere here. And improving the path loss could also be done using reconfigurable intelligent surfaces in order to improve the propagation environment. So both of these technologies goes into all of these factors here. So let's have some more concrete examples. When it comes to holographic MIMO, I haven't presented much mathematics in terms of rate expressions. And the reason for that is that it is basically a massive MIMO system. We can reuse existing theory, for example, from my book, Massive MIMO Networks. The important thing is that we need to utilize different channel models to get something that is physically accurate for the propagation environments of importance. We should not use ID Rayleigh fading models. And the asymptotic issues that people have been talking about for a long time, things like pulse contamination, computational complexity to be an issue, shuffling around data between different elements, we make measurement at one location and we're processing them elsewhere, that can be heavy to transmit at one point. These are issues that actually might show up now. They didn't show up in massive MIMO for 5G. But when we build holographic MIMO, where we have a large number of users and large dimensions, then all these problems will actually appear. And hybrid beamforming is something that I have been generally skeptical against, because why should we build a very advanced system and then throw away a lot of flexibility by just make it more complicated to implement, and it consumes more power, and just because it takes longer time to develop digital solutions doesn't mean that we shouldn't do it. And in 5G we will soon see digital solutions being utilized, also in millimeter wave frequencies. But eventually, when we are building very large arrays, you will have maybe 100,000 degrees of freedom, and you won't need all of them. So probably it will not pay off to have the ability to control all of them. So that's when hybrid beamforming like solutions can be implemented as well, but probably using metasurface technology instead of phase shifters, which is just a very bad solution in order to get an efficient operation because of all the losses. And in particular also the near field possibilities, where you can send many layers per users, which this also goes into the different channel models, will be important. That's something that we didn't cover at all in my book because we had single antenna devices. But if we go up in frequency, we can have multiple antennas there, and typically you only have one strong path, so you only use those antennas to beamform one signal, or maybe two signals using polarization. But when we go up in signal, even over line of sight channels, we can send multiple streams with different spherical wavefronts, and in that way we are able to separate more signals. So to say that we would like to reach 1 terabit per second in the future using holographic MIMO technology, how can we do something like that? Well, say that we have 50 megahertz of bandwidth, which is not very much, but it's in the 3 gigahertz band. That's a realistic number that we can get. Then, if we have a number of users from 0 up to, say, 40,000 users, or we have a number of antennas from 0 up to 10 times 100,000 is the number here. Then, as we increase the number of antennas, the sum rate in terabits per second goes up. And as we increase the number of users up to a certain point, we also have a sum rate that is going up. So one can, in the 50 megahertz band, serve a lot of users using many antennas. This is an example from a paper called Massive MIMO in sub 6 GHz and millimeter wave, physical, practical, and use case differences, where we were showing particularly about, say, we put up a lot of antennas on skyscrapers around Central Park, and we have a large number of users there. Then we can spatially multiplex them with all of these arrays. It's a kind of holographic MIMO scenario with 100,000 antennas and 10,000 of users, and all of them can be separated at the same time. So in these low bands here, we need to maybe multiplex 10,000 signal per site, and we probably need to utilize simple processing. Here I use maximum ratio processing, so it's the simplest type of method, and it still works out. And the good thing with being in low bands is that we have good channel coherence. The coherence time is long compared to other bands, so that's why we can serve so many users and learn their channels at the same time, as long as they are low build users. If we go up to 60 GHz band, use 1 GHz of bandwidth instead, well, then we still need to get a 1000 as our spectral efficiency, and we can achieve that yet again by having many antennas and serving many users, but not the same number. So we multiplex fewer signals, we use more bandwidth, but we still need to beamform again, we still need to multiplex users. So holographic MIMO can be utilized in all these cases to push up the data rate. Now someone might say, but wasn't the 6G target to achieve 1 terabit per second from one transmitter to one receiver? Yeah, some people have said that. I cannot really see the use case for that. I think the most important thing is to be able to deliver these huge data rates over a large number of users in the coverage area. You might need it in a backhaul link, but there are essentially no user applications of today, or that is imagined over the next decades, that will reach these numbers. As long as you can get a few gigabit per second, that will be enough for most use cases. Let's now shift focus and consider reconfigurable intelligent surfaces and compare it with technologies of yesterday, things that we already know. So I will compare reconfigurable intelligent surfaces with decode and forward relays, one of the classical relaying protocols. You have a transmitter called source using relaying terminology, and a destination, which is the receiver. And at one location here, 80 meters from the source, I have a reconfigurable intelligent surface or a relay. And I have 10 meters down here, and then I have a destination moved around at the distance d1 along this line here, which is parallel to the 80 meter line here. I'm considering that I would like to deliver 4 bits per second hertz. I'll use some channel models based on urban micro models. So I have a non-line of sight direct path, and I have a line of sight path from the source to this location where we have the relay or RS, and from that location to destination. So those channels are better, and that was based on the idea that we should deploy the surface to achieve that, as we talked about earlier. And here I'm showing the total transmit power that I need to use at the source in order to get these 4 bits per second in hertz. And what we can see is that if we don't have any extra equipment, I call it the size case, and the more I move away d1, the larger the power needs to be in dBm, and this is measured over 10 MHz of bandwidth. If I put a decode and forward relay, I get the blue curve, so I can lower the power a lot, and what the relay is doing is that it listens half of the time, and then it retransmits the data half of the time. and we are matching the powers to make it as power efficient as possible. So power is consumed both here, and then we get the blue curve over here, and we are varying D1 from 40 up to 100 meters. If I'm considering a reconfigurable intelligent surface here instead, I can go from 25 to 50 to 100 to 200 elements, and the more elements I have, the lower the power consumption becomes, because we can focus the energy more and more, and we can also gather more energy. So we have this squaring effect. And we can see that when the destination is here underneath, 80 meters away, and I have 200 elements, then I see a benefit compared to the mainstream DF technology. So we need a large number of elements to beat the relay. On the other hand, 200 elements, in this case where I have 3 gigahertz frequency, is something that fits into 1 times half a meter. So it's not physically large. We can definitely build something like that. But we should keep this in mind, that it's not in terms of signal-to-noise ratio improvements that the RIS technology is having the most benefits, but there are other use cases in terms of improving the channel properties more generally. So here's an example of that. I have a transmitter with 2 antennas. I have a receiver with 2 antennas. Essentially all devices from 4G and later have 2 receive antennas. So that is not something that is, is weird in a way. Then I have an RS located here, and it has n elements. And I have only a line of sight path here. So I only have a rank 1 channel because I have the same polarization at both transmitter and receiver. And if I now tune my RS to increase the signal-to-noise ratio, then I'm showing here the rate in bits per second in hertz as I'm going up in number of elements. And the black solid line here is when I don't have any RS at all, so it's just a constant value. I can see that if I configure the surface to maximize the SNR, under the assumptions that you can find this paper here, I need to have at least 50 elements before the RS actually starts to be effective. Remember what I talked about before, that when you have a small number, the direct path is much stronger, and when I have a large number, it's only the RS that is effective. But it starts at 50 when they start to contribute both of them, and then the SNR is going up. The gain here is not that large, so I think in those cases, if you would add a relay here and beamform a different signal to it, then it could retransmit it and you can get a better performance. The more interesting case becomes when I take my surface here and not try to maximize the signal-to-noise ratio, but to make the channel via the RS as different as possible, so that I can use my 2 receive antennas to separate them. And that is maximizing the capacity. Try to create a rank 2 channel with the 2 very distinctly different eigenvalues. And in that case, I only need, say, 15, 18 elements before the RS starts to be effective and increases the rate a lot. So here I'm focusing on improving the rank of the channel. And in general, I think improving the channel properties like that is when the surface is much more effective compared to conventional technology than only trying to maximize the SNR. So we should try to improve propagation conditions in general in order to make RS a useful technology. When it comes to wideband channel, I've only talked about narrowband channel. Here, one of the weaknesses with RS is also showing up, namely that when you have wideband channels, we have many subcarriers, and we will have different channels, each one of them. And RS can only select one configuration, so it needs to have the same configuration on every subcarrier, even if the channel is changing. So how can we select the right configuration in that case? Well, that is a computationally heavy problem, and it still haven't been solved properly. There are some algorithms that are looking for suboptimal solutions, and they are usually very computationally heavy. I will focus here on something called the strongest tap maximization, or STM, which is considered in 2 recent papers by other authors. And that is sort of based on at the RS trying to figure out which combination of paths in the time domain to the RS and from the RS is contributing the most, with the most energy, the strongest of the taps. So when you have a wideband channel, you typically have multiple paths with different delayed copies because the Nyquist criterion isn't satisfied anymore. And in these cases, we select the strongest tap. We are making that tap as strong as possible with RS, and then we hope that that will be helpful for the other paths as well. And here I can show you examples from a paper where we are considering two cases. One, when we have a line of sight path to the RS and from the RS. And what I'm showing here is the baseline when I don't have any RS. And if I don't have an RS in our system, we cannot just take away the RS and just ignore what would happen at that location. We always need to model something else at that location. Namely, here I consider either to have a metal sheet there that is satisfying Snell's law, or that I have something that is absorbing the signal energy perfectly. And they are essentially the same. So as I'm increasing my bandwidth here, my rate is going up linearly with the bandwidth, which is expected. If I can configure my surface perfectly in the sort of the upper bound where I can pick the RS configuration at every subcarrier optimally, even if that's not physically possible, I will get a red curve. And if I'm following the strongest tap maximization principle, I get this black dashed curve, which is very close to it. So when I have a line of sight channel above 2 and from the surface, I can configure it very well, even in wideband channels. And the intuition is that we are really utilizing that strong line of sight path. That is the one we are amplifying with our RS. And then that there are other scattered paths that are much weaker, we essentially ignore it. They get amplified in the way they get, and we focus on the strongest path. If I, from the transmitter to the RS, however, have a non-line of sight path, even if the user have a line of sight path to the RS. Here I show you the performance. The numbers are all reduced. I'm all sort of down to the blue curves here. The red curve, where I'm tuning the RS on every subcarrier, is giving us a higher rate. But the heuristic strongest tap maximization is almost indistinguishable from the cases without an RS, which is sort of showing you that if we should deploy an RS, we need to do it in a location where the transmitter and the receiver have line of sight channels to it, or at least they have dominant strong paths. Otherwise, it won't be effective. So that is sort of one of the weaknesses that we should remember when building systems based on these principles. Okay, when it comes then to deploying the surfaces in cases where we have line of sight to and from, what can we exploit the large surface area to do something beyond what conventional technology can do? Well, one thing is to mitigate fading through the utilization of channel hardening. So when we have a large surface area and we have a fading variations along the surface, they will vary at the same pace as half the wavelength, as we were considering earlier when we were describing how many degrees of freedom we're having. So we essentially can use those degrees of freedom to cancel out channel fading variations and get a more stable communication performance. This is something that we are characterizing in this paper as well. One can use it to counteract Doppler effects. So if you have a transmitter or receiver that is moving and you have an RS that is at a fixed location, but we know how the transmitter or the receiver is moving, we can shift the behavior of the surface in such a way that we are cancelling out the Doppler effect. And this is described in this paper. Also a cool kind of phenomenon that cannot be utilized with conventional surfaces. And then we have the thing with macro diversity. We can increase the rank, as I was exemplifying. We can potentially mitigate blocking. So in particular in millimeter wave band, or what we call sub-terahertz band, where signals are having large bandwidth, which is useful if we have a strong signal, but they're also sensitive to blockage. If we can put up surfaces all around ourselves, then what we can do is that if the signal gets blocked from one direction, there is a surface from another direction that reflects the signal towards you, so that we can always have a strong signal wherever you are. Okay, so should we compare reconfigurable intelligent surfaces and holographic MIMO? Well, we can do that. Let's do that. Say we have a source transmitting to destination. We have a surface over here. We have, for every element in the surface, we have a channel gain of path loss alpha, and then from every surface element here to destination we have a path loss beta, and now we assume that this direct path is totally blocked. And I will either consider having a reconfigurable intelligent surface here, or a massive MIMO or holographic massive MIMO surface here. When we are using the RS technology, then I have a transmit power that I call rho here, so it's not the direct path's loss anymore, it's the power, or SNR. I have the number of elements in the surface here squared, and then I have the product of the two path losses here, just as we have considered earlier. If I take this expression and just split it up into two parts, I have rho, the transmit power, times number of element, times beta, which is the path loss here, then this will be the sin to noise ratio that I will get if I consider this holographic massive MIMO transmitter using the same power, and I transmit with n elements, so it has the same number of element, to the destination here. So that is one of the factors showing up in this SNR. The other factor, what remains, is one n and one alpha term. And this is the fraction of the transmitted power from the source that gets lost over the air. Sorry, not what gets lost, but what is received over the air here. So this factor here is always smaller or equal to 1, because at the best case we have such a large surface that what we transmit here, all of it will be received here. So what this shows is that the SNR that I get with the RS is always smaller or equal to the SNR that I get with the massive MIMO system if I put it on the same location here. So we can show the kind of behaviors here, for example. The total channel gain, which is then n times beta with massive MIMO, and n squared times alpha times beta with the RS. And I am 25 meters from this location to the destination, and I'm only 2.5 meters from the source to this surface here. So if the source is not a massive MIMO transmitter here, but a user or a device closer to RS, it's still very close by. We can see here that with massive MIMO, I get the red curve here, and with an RS, I get this black and dashed curve going up here, like this. And it has a bigger slope because of this n squared term here, but it starts at a smaller number because of this loss here. The additional n here is not really a benefit, but it's also showing how much we are losing along the way here. In the best case, n times alpha becomes equal to 1, then we are not losing anything at all. So the point here is that an RS will always have a worse signal noise ratio than a holographic massive MIMO system for the same number of elements. So it's really about that we should deploy the surfaces not as a replacement for massive MIMO, but in order to say that, well, maybe we cannot afford to put up a big base station here, so let's move the surface to a different location, and maybe we can trade away also so we could put a larger surface there, because it's a passive kind of surface where we don't need as many components for it to operate. The last and second open problem that I would like to talk about has to do with channel estimation. So everything I described so far is about focusing energy at locations or in directions when we know the channels. How can we learn the channels? This is a particularly complicated issue when we have a reconfigurable intelligent surface. For a holographic MIMO, well, we know. You can read all the textbooks on the topic and understand how we should estimate channels. But the RS is blind. It's only supposed to take energy and retransmit it. It cannot measure things. Well, we can have a solution where we say a fraction of our RS element will be active, contain receivers, so we can measure signals at the fraction of them. But the problem is that if you have 1,000 elements, and then you say, I will only need like 5% of the elements in order to measure the signals, then 5% is still 50 elements. So it's still like a massive MIMO base station. So we cannot add active RS element without removing the whole low-cost, simple, passive kind of idea with the RS technology. So we need to develop methods where we estimate the signals elsewhere. And that can be done on the codebook level. So we can have a user here that is repeating a known signal, a so-called pilot signal, and then we let the surface circle through some different configurations. And for each configuration, the base station is measuring the channel quality, then it solves an optimization problem to figure out what configuration that is preferable, then it feeds back this information to the RS controller. And in that way we are then switching through configuration, find the best configuration, and then we utilize it. And let me explain now briefly how the estimation would happen. So remember, earlier we took this channel model that we developed, we divided it up into different parts. We had the direct path, we kept it, then we had the product of two vectors describing the channel vector 2, this is 2 and this is from the RS. And we actually don't need to be able to separate these two different channels because we only observe the cascade of them. So we call this vector G and it's n-dimensional. And here we have a controllable vector. So when I'm transmitting a signal, x of n, the received signal, z of n, will be x of n multiplied with the direct channel h, which is a scalar. And then we have the inner product between G and omega, which is the name I give this vector that we can control. Omega and theta is a subscript. That is what we can control in particular. So this is the received signal, and here I have noise. Say that we are repeating the same pilot L times, and I call this pilot signal S to keep it simple, so it's S as in signal, and every time I transmit it I use a different configuration. So omega with theta 1 up to theta L, these are my L different configurations. And remember, this is how I wrote the received signal. If I now gather the signal that I will get at time 1 to L when I replace theta with theta 1 to theta L, then h is the same all the time, so it's h multiplied with 1, 1, 1, 1, it's always 1. And then I have the signal S. And then I have G transpose, I have omega theta 1 to theta L multiplied with the signal S. And then I have the collection of all of my noise variables like this. Let's say this is a vector with received signal, or a row matrix. Here I have omega collecting the matrix with all of my configurations as columns, and here I have a row vector as well with all of my different noise signals that I'm receiving. Then I can rewrite this entire thing as z is equal to this plus the noise. I have the signal, and the signal is multiplied. Let's take h, which is the channel that I would like to know, and g, which is I would like to know. I can write this as h times g. H transpose should be multiplied with the 1, 1, 1, and transmit doesn't mean anything when you have a scalar. And G transpose should be multiplied with omega. So this is the signal I'm having. Okay, so now I observe this, and what I would like to isolate is this channel that I have here. If this matrix here with 1s and then I have omega underneath, if this is an invertible matrix, just suppose it is, let's call it omega tilde, then I can multiply this entire expression with omega tilde inverse from the right hand side to get rid of this matrix, and also can divide with s. In that case, I get omega tilde inverse, I get s inverse. I have isolated the desired channel vector here, and then I have some scale version of a noise here. And this is a channel estimate. Now I know the channel. Up to some noise here. So if I just transmit the signal strong enough, this term here becomes small and I get a good estimate. The problem with this entire thing is that I need this matrix to be invertible. And since this is a vector of length n plus 1, I need this matrix to be n plus 1 times n plus 1 in order to make it invertible. We can do that if we transmit n plus 1 different times, and we select omega as tilde to be a DFT matrix. I mean, the first row of a DFT matrix is 1, so this would then be the DFT matrix. Then we can achieve it. And every element have unit modulus, so it just different phase shifts. So we can implement that. But the problem is that if we have 1,000 elements, well, then we need to transmit 1,000 plus 1 times in order to estimate the channel, which we might not be able to afford. So what we could potentially do is to simplify the entire estimation problem using channel sparsity. And we know that channel sparsity exists in G, and I have already described this type of things. How we can model it, that there will probably be dominant paths. But it's still an open research challenge to utilize this structure in the most effective manner, particularly because we have a cascade of channels. So we should definitely use sparse channel models. We can potentially group some neighboring elements together and say that these elements should have the same configuration. If we group every 10 elements together, we can divide the number of pilots by a factor 10. But there's still a lot of research to be done. You can find in my paper, Reconfigurable Intelligent Surfaces, 3 myths and 2 critical questions, and description of methods that can be utilized for channel estimation. And in the prototyping papers that I was describing earlier, with this surface here with 1,100 elements, well, the way of simplifying the configuration here is that some elements were put together, and then there were a simple algorithm where all of the elements started with the same configuration, and every element only have 2 states, plus and minus 90 degree. And then we went through every row and checked, is it better to have it +1 or -1, or plus 90 degree or minus 90 degree. And then we chose the best option, went through the next row and tried it out sequentially. Then every column was tried out like that, and now the overhead becomes proportional to the number of columns, number of rows. We add them up, and that is what we're getting as the complexity, and not something that is multiplied with them, which would be needed in order to figure out the total number of elements. So in summary, what I've been talking about is development of future technology. And in general, we can think about it like this. Conventional technology have operated in the sub-6 GHz band using passive antennas, or antennas with very few number of active elements. 5G is covering massive MIMO with 64 antennas or so, and millimeter wave bands, but to be honest, the dominant part have been to still work in the 3 GHz band and use massive MIMO technology. Eventually, millimeter wave technology might be used to a large extent. We don't know to what extent it actually will be utilized. But there seems to be sort of a general feeling that, because 5G is so much about millimeter wave, it will go up in frequency in the future. That's probably true. We'll do that in some niche applications. But I'm very convinced that this is not going to be the main thing beyond 5G, just as millimeter wave is not the main thing in 5G. It's barely used so far. I believe that it's up here with having even larger arrays where we will see the big improvement in the future in order to get more stable performance and be able to spatially multiplex many users. So the future requires large arrays, and it could be in the form of holographic MIMO, where we get a massive number of spatial degrees of freedom. We need to have many active components to build it. We can also have reconfigurable intelligent surfaces, which are simpler surfaces, less component. We only are tuning different impedance values, but it can be a challenge to control it and to tell it how to control it in the best way. So there are many interesting research directions for all of these methods, and a lot of fundamental problems are already still remained open. And as you have noticed in this talk, I've focused a lot on the fundamentals. There is particularly many open problems in the fundamental problems, I think. There are many questions that remains to be answered. There's a large number of papers that are considering very contrived combination of different concepts. You add an RAS, and you add a UAV, and you add this and that, and you consider IID radially fading channels, and things that are not very relevant, I would say. I think we should really go back and think about the system models, the channel estimation, utilize sparsity, make this work well in the simpler setups, and identify the good use cases, and then we can add additional aspects on top of it. So when should we use which technology? I would say holographic massive MIMO is really the great thing in order to spatially multiplex many users and utilize near field effects where you can multiplex many layers per user using spherical wavefronts, or have the possibility of serving many different users in a rather small area. And it works with any propagation environment, so that's one of the great things. And scattering might even be a good thing for this technology in order to get the richness needed to spatially multiplex many users. Reconfigurable intelligent surfaces is particularly about coverage, extension, reduce fading effects, and improve channel ranks, improve properties of channels in general. The issue is that we need to deploy them so that the transmitter have a line of sight channel to the surface and the surface have a line of sight channel to the user. Otherwise, the benefits will be very small, because you will have a direct path that might be equally strong. So you need to have a huge number of elements before the surface becomes effective. And you also have the issue with that you don't want to have much frequency selectivity, because we will utilize the surfaces with wideband channels, so there must be dominant paths that we can lock our configuration on to amplify those paths, and not have many weak paths. Then the surface is not effective either. So here are some key references that I think of interest. So in terms of overview papers, one of the earliest ones was Massive MIMO is a Reality, What is Next? 5 Promising Research Directions for Antenna Arrays. I have a new paper that is providing you with more details on a lot of the mathematics that was presented here. Here are some other papers about myth and 2 critical questions. Here is a great survey paper by other authors, Smart Radio Environments Empowered by Reconfigurable Intelligent Surfaces. When it comes to channel modeling, I recommend these 2 papers. When it comes to prototyping of RS, here is the paper that I was mentioning, which you find in archive. And when it comes to holographic or MIMO or large intelligent surfaces, I recommend these papers in particular. And here are some papers that I have been part of as well. And in general, many of my papers that have been published in this topic is also published along with code that you find on my GitHub page. So you can download that and try out if you are starting research in this field. I would like to end by thanking you for listening and staying all the way to the end of this tutorial, and I would also like to thank all of my collaborators. So with that, if you would like to hear me talk more about this technology or other technologies, you can check out my YouTube channel, Wireless Future, and my podcast, Wireless Future. Thank you very much for attending.